like hydraulic fracturing or the fundamentals, and what are the main engineering principles behind the design of a fracturing job. I'm gonna touch base on that a little bit, but feel free to uh, jot down your questions, and at the end of the presentation we can address those. So my idea is to give you a very broad overview of what we are doing here. So let me share my screen really quick, then we can get started whenever you guys are ready. And yeah, so just let me know, Watek, when we can start.
Yeah, we are ready. You can go ahead.
Oh, really? Okay.
Yeah.
All right. So just to preserve the internet connection, and if you don't mind, I will turn my camera off, or if you prefer me to have it on, I'm more than happy to,
No,
whichever
it's
way.
up to you. It's up to you.
Okay. Yeah. So I don't mind having it open. All right. So as I mentioned, as Watek mentioned, today's presentation is going to be about the identification of those factors that are affecting production from unconventional reservoirs, more specifically from multi-fracture horizontal wells. So you can think of these as those factors that are actually pushing the fluid out of the ground into the wellbore. There is so much implications for them. There is so much to study, and for this particular presentation, I wanted to condense the main points, the biggest points, for you to have a very grasp as to what's going on with unconventionals. So here's a picture of the U.S. I personally love this picture. Is from NASA, actually. And I was looking at over it the other day, and found it interesting. First of all, how a little bit dispersed is the U.S., right? People like the eastern U.S. more. I can see that, right? And we can look a little bit more further, and let me show you guys a little bit of the U.S. Over here, we have Houston. This is where I'm at right now. This is our city. It's very close to the Gulf of Mexico that is over here. And also we do have Dallas right here. So it's about a 3.5-hour drive from here to Dallas. So it's not too far from here, from Houston. Over here, we have the capital right here. Austin, Texas is also not too very far. It's like a 2.5 hours drive from Houston. Down here, we have San Antonio. So, you can imagine this is Texas over here, and in these places you have Midland and Odessa, other cities you might be interested in, and I'm gonna show you later on. And over here, just for the reference, you have Chicago, right here in Lake Michigan. And over here you have Atlanta. This is the place I flew a month and a half ago from Colombia. We landed in Atlanta almost 2 months ago, actually. And here's beautiful Miami, New York over there. So this is to give you guys a perspective. And then if we zoom into this particular region area of Southwest Texas, we see these cities, right? So we have here Houston, Gulf of Mexico, Corpus Christi, Laredo, San Antonio, etc., and Austin. But I want to bring your attention to this area over here. So can you see this? How big this patch or these lights over here are compared to these distances? Well, this is the Eagle Ford Shale. So I hope that this gives you a perspective as to how big the activity in this particular shale is here in the United States. It's really huge. There's so much going on, not only in that patch, not only in the Eagle Ford, but there are others that I'm gonna show you shortly. But overall, this is the previous picture that we had. And here, if you know this little patch, relatively little, you can, compare it with the size of Houston over here. This is the Bakken. So this is another shale basin that is it's been very, very active here in the States. So that this is to give you guys a little perspective as to what's going on. And Canada is over here, so you can imagine that this is activity going on in the Canadian area or region. This is also a snapshot of how the shale activity evolved in the Eagle Ford. Particularly, we're looking at Cotulla, Texas. This is a picture also from NASA from 2000, and then some years later, almost 5 years later, this is what you get. And all of these are multifracture horizontal wells. So there is plenty of those wells in the Eagle Ford. And in fact, if you look at the scale over here, it's 5 kilometers, 5 kilometers. So this is huge activity. And this is just a tiny part of the Eagle Ford shale. Other parts of, of your interest when you think of unconventional reservoirs is the Permian Basin. I know perhaps you have heard about the ongoing activity in this basin. It's huge. I have had the opportunity to go there several times, and oh man, it's incredible. Last time I drove by, you could look, you could see all rigs, drilling rigs, wherever you look at. And there was a drilling rig next to a highway. It was funny, but that's what the industry looks like in West Texas. So here we have Midland and Odessa. All the operations are essentially centered here in Midland for West Texas and Carlsbad, New Mexico. I also had the opportunity to be there for Southeast New Mexico. Huge activity over there. So, and to give you a really broad view of how the oil industry evolved for the past 20 to 30 years and how it changed, I want to show you this short video. Let me see if you, let me know if you can see it correctly?
Yeah,
okay,
it's
good.
interactive.
All right, awesome. So here, you can see how Saudi and Russia were dominating the market in the early 2010. And then here you are, guys. And this is what the production in late 2018 looked like. So you might wonder what boosted that production from the United States. Shale oil and gas. It's undeniable that having created or adopted that technology to tap those unconventional resources was definitely a game changer for the United States, and it's going to be for the countries that are pursuing to develop these unconventional resources, and the U.S. has plenty of them. I was talking about the Eagle Ford earlier over here. And here's the Permian Basin. Is a huge basin. The Bakken right here. Remember I showed you guys this one that is in the limits with Canada. We have plenty over here in the Denver Basin, Niobrara, Powder River Basin over here with the Marcellus Shale. Is a huge shale basin over here in the Appalachians. Is actually close to New York, relatively close to New York, and Pennsylvania, Utah. Excuse me? Okay, no problem. And so there's plenty. We went to college over here in Texas and in Louisiana. So we have the Tuscaloosa Marine Shale just passing by over here. Main basins, we have Permian, Eagle Ford, Haynesville, Anadarko, Niobrara, Appalachia that I just mentioned. This one is mostly dry gas. It has some gas condensate, some oil, but not as much as they produce gas and the Bakken. So these 1, 2, 3, 4, 5. These 5 over here primarily oil producing patches, and these 2 are primarily gas producing patches. The outlook of the only country I had access information for, comparison purposes. So this is how each of these basins are contributing to total oil production, okay? So as you can see here, the Permian is a huge contributor and is expected to remain like that for the years to come. So compare the Permian with the Gulf of Mexico. So it's incredible the amount of oil that you're producing from these unconventional reservoirs. Here's the Bakken. So the Bakken alone produces as much or almost nearly as much as the Gulf of Mexico. And look at Eagle Ford, Niobrara, Anadarko Basin, and the rest of the United States. So this is for you guys to get to see how big this industry is. I'm speaking about unconventional reservoirs and the outlook. Even for the bad low oil and gas supply case, which is the worst case scenario, tight oil will continue to dominate the market at least until the 2015s. So it's here to stay. We gotta be, on top of things. I know that there are some new engineers in the audience, so bear this in mind. We gotta be sometimes switching gears to get to understand what's happening at the economic level, so that we don't lose sight as to where we are as of today in our industry. So for the agenda for today, that was a very brief introduction. So today I'm gonna talk about five main topics. We're gonna start with the concept of what is a performance driver, what we used to call them in conventional reservoirs, so that we made the transition more smoothly from conventionals to unconventionals. Why is it that these models don't work, namely on unconventionals, and then we switch our focus to the fundamentals of hydraulic fracturing, and followed by completion design in unconventional reservoirs. Why are these things challenging? What we engineers have done so far in regards to producing from unconventional. Why is it so successful? Why is it that we are seeing this crazy amount of oil and gas coming from these basins? And then we will touch base on fluid flow in porous media, so the fundamentals of rate transient analysis, fluid dynamics in multi-fractured horizontal wells, and how they affect productivity from these reservoirs. And lastly, we'll touch on, I hope that I can get there, I'm gonna move as fast as I can. We'll get to field case study that was for a well in the lower Eagle Ford, so that you guys have a better, it's like a summary of the presentation. Everything will be condensed into a few slides for this particular well. So let's start with the concept of performance drivers. So let me jump right into it. So conventionals versus unconventionals is going to be the first part, and then we will take a look into the material balance equations. And okay, so let me stop about the recording. Watek is taking care of that, so let's do it through Watek. And then if you have questions about the presentation itself, please feel free to reach out to Watek, please. I appreciate it. So as I was saying, we'll start with making this very brief comparison between conventionals and unconventionals, and then we'll look into material balance equations, the concept behind them, what is transient flow, what is boundary dominated flow, what are the differences between them, and why it's important to account for flow regimes when you're making these calculations. And then we'll take a look into performance drivers, or what we used to call indices in conventional reservoirs. Here's again is a very, very broad picture of conventional versus unconventionals. I believe you guys should be very familiar with this picture of a conventional reservoir over here. Conventional reservoirs being really, really affected by hydrodynamics. So how fluids move in the subsurface can really affect a conventional reservoir, right? We know that gas caps will form as we drain fluids from oil reservoirs. So the cap gas drive can have a really huge impact on oil production, particularly during the primary depletion stage. Uh, but in those reservoirs, we also have tight gas reservoirs, are very similar to shale, what we call shale oil and gas. And overall, the main difference from the geological perspective between the two, leaving aside permeability and porosity, main difference is that unconventional reservoirs are barely affected by hydrodynamics. So what that means is that volumetric calculations, as we know them, perhaps are not the best way to go. So we cannot use material balance equations or decline curve analysis for unconventional wells. And we'll talk a little bit more about decline curves later on the presentation. And lastly, the only way we have seen right now to analyze production data to make performance or forecasts and production forecasting is through reservoir simulation. It's really the only thing we have available to us for making inferences about production performance in the long run for unconventional reservoirs. So this is all achieved through multi-fracture horizontal wells. Sometimes you will see it as MFHW throughout the presentation. And it's essentially consists of a very long well, sometimes very long laterals, which, here in the US, they can reach up to 2 miles. So 2 miles, let me make the conversion. So is around 16 kilometers. So they are 2 miles, 4.2 kilometers. Sorry about those, something like that. I was making the wrong conversion.
3.2 kilometers.
3.2 kilometers, there you go. Sorry, thank you, Watek. Yeah, I don't know what, I use a different conversion factor. That can happen. You gotta be very careful with the conversion factors, guys. So it can be, so you can imagine a 3-kilometer long well being fractured in multiple stages at multiple places. So it creates, first you get the hydraulic fractures that they will be generated, they will be created in each of the stages. But apart from that, you will create some fracture complexity around the wellbore. So it really depends on the rock quality, whether it's very brittle, very ductile. Rock properties here, as well as like in conventional matters a lot when it comes to hydraulic fracturing. So the fact that permeability is very low in these reservoirs tells you that these wells experience very long transient flow, and you will see why is this important. But just keep in mind that low permeability, induce very, very sharp pressure gradients, and then the pressure tend to drain slowly but very sharply, so that induces very long transient flows. Some of the challenges: fracture geometry. It's very open to discussion, because some argue that you don't even have any planar fractures like the fractures we know. You just have a bunch of fractures like this. Some others say, no, yeah, we have evidence that there is planar fractures. So fracture complexity is a very, very big deal on unconventional reservoirs, and of course geomechanics. So by geomechanics, we refer to the fact that these reservoirs, as everything in the subsurface, is subject or under stresses because of the overburden, basically the weight of the rock acting on the formation, so that it tends to compress or to stretch depending upon the stress regime. We'll touch base on that too. And therefore, hydraulic fractures, or these fractures when they don't have any support from within, because the initial support is the pressure itself, the fluid pressure that keeps these fractures open. When you start draining that pressure, fractures tend to close. So that's what we call geomechanics. Okay, so to relate this, what I'm talking, I was just talking about transient flow regimes in conventionals. Let us do a refresher over here. So here is just a conventional reservoir. You can think of this. This is the cross-section view. So you can imagine this is a square reservoir, rectangular or circular reservoir. It really doesn't make a difference for this comparison that I'm going to make. So when we start depleting the reservoir, we have a pressure gradient, right? We have a pressure distribution with it, and it's more or less uniform depending upon reservoir properties. Again, if it's more or less homogeneous, pressure will behave like in a symmetric way. So you have a pressure that depends on a radius and time, right? But as pressure travels at early times, you have a pressure disturbance going up to this point, but really you have not seen much of the reservoir. So having a closed reservoir at this point, like you know what's the size of the reservoir versus not having it, does not make really doesn't make a difference, right? Because the fluid as the pressure behaves as if the reservoir was infinite, right? Like pressure travels like if it was inside or within an infinite media. So that's what we call transient flow regime. So reservoir size really doesn't affect pressure. And then the reservoir boundaries cannot really be seen during this transient flow period. So therefore, as a consequence, if you don't know how big the reservoir is, you don't know, or you cannot guess to a high degree of accuracy how much oil and gas you have down in the reservoir. But later on, when pressure had depleted for so long, you have this type of behavior now. The pressure has, reached the boundaries of the reservoir. So now you know the size of the reservoir. So at this point where you get to that time where, pressure begins to deplete around the reservoir uniformly, more or less uniformly, is what we call boundary dominated flow. And then at this point, for us reservoir engineers, or for engineering purposes, we consider the reservoir as a tank, right? It's a closed tank from within which, we have a finite volume so that we can estimate the original oil in place, original gas in place, water in place. We can do these calculations as I'm gonna show you. And the good thing, or the inventive way we had handled this problem is that instead of having these gradients, which we know they happen because that's what mathematics tells us, we can consider an average pressure. So we have the special distribution. So we say, the average pressure over here is more or less this. So unlike the pressure that changes depends on the radius and time, the average pressure really depends on time because it's an average value, right? One nice property about the average pressure is that it changes. The pressure is not average, but the pressure at this point changes with radius in a constant pace. That means that pressure here drops a certain amount by a certain amount, and then everything else will drop by that amount at the same time all throughout the reservoir. That's what we call boundary dominated flow. So this finite volume tank type of, I'm sorry, is that me? No, sorry about that. Okay, so let me clear my screen over here. So yeah, I think I was okay. Anyways, so at this moment, when you have boundary dominated flow, you can consider the reservoir as a tank, and then you measure whatever is happening within the tank using the average pressure. So you can calculate the average density, average viscosity, average permeability, all of that on an average basis. So as I mentioned, the reservoir size can be estimated. Therefore, you can apply simple material balance equations to estimate what comes in and what goes out, right? So material balance equations is just simply that. It's just a method to determine the original fluids in place. Is based on production and static reservoir properties. So because it's a zero-dimensional reservoir model, meaning that you don't have any transient flow going on, you don't have really properties varying spatially. So you can basically do this. This is a kind of a representation of your typical tank calculation. So you have oil in place, your initial gas in place, your initial water at the initial pressure. Let's call that pressure pressure one, right? So if you drain pressure, as you will do, otherwise you won't produce, excuse me, so when you drain pressure, the reservoir will, or your tank, should say, should look like this. And then over here I have, this should be minus, okay? So let me see if I can correct it really quickly. Okay, And I'll go back so that we don't get confused. Um, so yeah, this is pressure, right? That is lower than the initial pressure. So at this point, you produce some oil, perhaps some gas that is, dissolving oil, but then the gas expanded, the rock is expanded, the water expanded, and if you have an aquifer, water had encroached. If you are injecting gas, well, gas had been, pushing the reservoir because of the volume that it occupies. Okay, that it occupies. This is, in a nutshell, what happens with material balance. Why is this important for this talk? It's because here we define our drive indices or the performance drivers for conventional reservoirs. And there are four main drivers in conventional reservoirs, namely the depletion drive index. It's basically how are we producing what amount of production is due to oil expansion, right? We know that oil is compressible to some extent, mainly due to gas dissolving in the liquid phase. So as we deplete pressure, the fluid tends to expand, right? And when that happens, this is what we call the depletion drive index. And now we have the cap drive, gas cap drive, which is basically the gas expanding and then pushing the oil out of the ground. The water drive index is also important. It's basically how water is, pushing the fluids out of the reservoir. And compressibility index is what I showed you, where, fluids expand like water expand, and then the rock itself expand because of the pressure withdrawal from the reservoir. Next, right, unconventional reservoirs. So this is where the fun begins. In unconventional reservoirs, we are looking at different things. I mean, compared to conventional reservoirs, first of all, we have to deal with ultra low permeabilities. We have to deal with very long transient flows. So we don't, we're just talking about all of the wonders you can do with material balance equations, determining which index is having the most impact on production, whether it is water injection, whether it is fluid expansion in the case of primary depletion, whether it's gas injection that is driving your production. You can get to know all of these things when you have reached boundary dominated flow. But, I'm sorry, I don't know what's happening over here with the screen. Okay, anyway, so
yeah, don't worry.
When we deal with this type of reservoirs, really estimating how much you can recover from your well becomes challenging, because if your fluid is in under long transient flow, it's going to be very, very hard for you to to guess how much can you recover. This is this chart, I love this chart. Is really informative. It shows you what is the difference between, impermeability from conventionals to unconventional reservoirs, right? We used to call, or we typically call this region over here, we call it the shales, right? The extremely tight reservoirs. We call them shales. In reality, they might not be shales, just mud rocks or very, very, very tight sandstones or carbonates. There are very different types of these extremely tight reservoirs. So for you, and then we have very tight, and then we have tight reservoirs. So for you to have a sense of, the magnitude of order of magnitude difference between these, here the scale is in millidarcies, right? So a microdarcy will be over here, right? So it's 10 to the minus 3 millidarcies. And then we have over here nanodarcy scale, 10 to the minus 6. And then you think, oh man, this is almost impossible to produce from these wells. And then look, where's the Haynesville located at? Where is the Barnett Shale, Marcellus Shale, Fayetteville, Eagle Ford, which is a really good one, really nice one. We also have wood for Utica and many others. So the idea again is, to produce from these reservoirs using completion techniques like multi-fracture horizontal wells. We already mentioned this. This is a schematic of how a multi-fracture horizontal well looks like. It's an ultra-low permeability system, as I mentioned. And so typically, this is what you would expect to encounter in these wells. So you have the hydraulic fracture, which is the planar fracture that you have here. We reservoir engineers like to represent it as a perfect planar fracture, which is symmetric with respect to the wellbore. It's nice, it's self-contained within the formation of interest. But we also have this simulated rock volume. What is it? The simulated rock volume, as we're gonna take a look later on, it's about cracking or creating this fracture complexity around the main hydraulic fracture. And not surprisingly, most of the production from these wells are coming from this region. Hence, or therefore, it is very, very, very important to get this fracture complexity done right when we are completing the well. But one of the things is that we have somehow little control on how these fractures will grow laterally, how these cracks will eventually grow laterally. There will be several factors involved in it. We have natural fracture networks that might be existing in the reservoir, but that they are sealing or dormant. So hydraulic fracturing will reactivate them, but there are all risks associated with that, which will be, for instance, if you have a natural fracture network that is active, your fracturing fluids will be going through those networks preferentially under certain conditions, so you don't grow that fracture complexity as much. So basically, or essentially, when we talk about unconventional reservoirs, the reservoir contact area is key. How much of the reservoir we get to contact through hydraulic fracturing is fundamental, is key in how much we will produce from these reservoirs. And namely, multi-stage fracturing is naturally a key factor here, as well as reservoir free properties, because that will tell us how good will the fracture look like from a mechanical perspective or from a rock mechanics perspective, on how fluid will move within these fracture networks. That's from a fluids properties perspective. And finally, we have completion properties, as we just discussed. So here, from now on, we're gonna be looking at different topics, right? Where I'm gonna show you how to determine those performance drivers in unconventional reservoirs using physics-based modeling. So earlier I showed you that you can use material balance calculations in conventionals. You cannot do that in unconventional, so we got to look at a different type of analysis. For that, we will require pressure and production history. It's fundamental to understand what's happening down in the subsurface, so that we are like the doctors of the reservoir. So we have our instruments here in the reservoir, listening to it, looking at what's happening down there, in order for us to predict how much oil or gas can we produce from that reservoir. And that goes paired with what we call rate transient analysis, right? So in the end, we look for getting an accurate estimation of the ultimate recovery. Okay, so we will begin with the fundamentals of hydraulic fracturing. If you want, what you let me know. We can have 5-minute break here, just to to get ready for the next section, and I will wait if you want. What do you think? Watek, can you hear me? Watek? Okay, so if everybody's fine, we can take a 5-minute break. We'll retake it at 8:40 local time, 8:45.
Okay, no problem. No problem. Okay, we can
It's
return
okay?
back at in our time at 4:50. So it will be
Okay.
8 minutes.
Yeah, okay, let's do 8 minutes, and then we'll retake from here, because it's gonna be a little bit heavy on this side on the elf, right? So in that way, we will improve our flow capacity near and around the wellbore. So that is very, very important, particularly for low permeability reservoirs. So let's, this is just a very rough representation of a squarish reservoir with a well in the center of it. And here is uh, again a representation of how the pressure changes or distributes within this region. And as you can see here, there's a huge amount of white, well, not huge, but you can really see a big amount of white near the well, but other areas are more or less reddish. So this tells you that there are large pressure gradients near the wellbore, which is typical of low permeability reservoirs that don't have stimulate any sort of stimulation. But we also have poor contact with the reservoir, so there is so much fluids left behind because pressure cannot reach those regions, right? And even so, you will need a huge pressure drawdown, a huge difference in pressure from here to here in order for fluids to fluid, if at all, right? So when you think about fracturing, what fracturing does is basically it enhances this region. So you have heard about the equivalent wellbore radius when you deal with hydraulic fractures. This is more or less the concept, right? So you have a fracture, a bi-wing fracture. Again, we assume is nice, is bi-wing, symmetric with respect to the wellbore, but that's not what's important. What's important is what happens around the wellbore. So you see that now over here, the gradients are lower than this. So you have more whitish or low pressure areas surrounding the well, which tells you that there is a lot of fluid, additional resources coming from these regions over here. So you can think of this as this, right? So now you have this fluid flowing this way. And then naturally your productivity is going to increase because of this. Right, so this area where you have a bunch of fluids coming in is what is going to be of our interest, and we will discuss much more, believe me, much more about it in a little bit. What is the conceptual, or what is the concept behind hydraulic fracturing? This is a rough schematic of how fracturing happens in a conventional well, in a conventional reservoir. So you have your vertical well. It can be a slanted well, but the purpose here is to compare how these, to show you how this goes in a conventional environment. So you have your well is cased in this case. So you have your perforation. So you basically create holes in the casing, right? And then typically you will install a mesh screen over here or a slant mesh, which again, you typically fill with propant or with sand or gravel is actually the word I was looking for. You fill this with gravel. So this is what's called gravel packs, right? And then if you fracture this region, fractures can grow for as long as we want. We will discuss more about that too. And this is how you get your fractures there. Two important concepts here are target formation and the stress barriers, right? So when you put high pressure fluid inside the wellbore, inside of the wellbore, and then you start pumping into the formation, and then you start extending these fractures, what is gonna keep your fractures in place, or as nice as you see them here, that they are self-contained or contained within the target formation, are these two formations. This is the overlying formation and the underlying or the underboard formation. And this is called, these two are called, from a geomechanical perspective of rock mechanics perspective, they are called stress barriers. Oftentimes you find that these two given the history of the formation, given the geological setting of the formation, these two have higher stresses than the target formation. So that, no matter how much, well, it doesn't matter, but you can put a lot of fluid within this target formation and then it will grow your fractures laterally, not vertically. There's where we have troubles. When the fractures start growing vertically, we start having troubles. So things to consider when designing a fracturing job: rock mechanics. We have to have a good understanding of, what are the stresses in the reservoir that I'm looking at. You got to look at rotation stresses, well, not rotation, but orientation of those stresses. Where will fractures grow towards, in which direction, and then how much do you need to grow your fractures? And that's gonna be told by the hydraulic fracturing propagation models. There are several models to kind of come up with initial design for your fractures. There are 2D models, 3D models, pseudo 3D models. We will discuss them shortly. And finally, you have the treatment design variables. So that has more to do with the fluid, right? What type of fluid, what kind of fluid, how viscous it is. Is it going to be cross-linked? Is it going to be, has special properties? All of the additives that they have. Is it going to be slick water? And also the propane. Is it going to be ceramic propane? Is it going to be resin-coated propane? Is it going to be sand, just white sand? And it really depends on the formation. But overall, these are the major design parameters that we are going to be working with. So to begin with, let's take a review on rock mechanics. When you talk about rock mechanics, you are simply talking about stress regimes in the earth, in the subsurface. So it all started with Anderson's theory of faulting back in the 1950s. So they were trying to figure out how stresses behave in the Earth's crust, right? Why there are normal faults? Why are there reverse faults, truss faults, strike slip faults? Why is it, right? So if you think about it, well, one rock displacing the earth like this or laterally, it has to do with the amount of force you put in the different directions, right? So normal faulting occurs when the overburden stress or the vertical stress is higher than the maximum horizontal stress or the stress in the horizontal direction, which at the same time logically is greater or higher than the minimum horizontal stress. And this is one of the main or the most important concepts here, is what we call the minimum horizontal stress. This is also called the closure stress. And again, we will discuss more about it shortly. Then another thing we have here is strike slip faults. So strike slip is when the vertical stress is not the maximum stress. So it's really difficult to think about it, right? Like the overburden of the earth, the weight of the rock is not the biggest stress, but lateral stresses are. And it has to do with tectonic stresses, what the faulting regimes are in a certain area. Same goes with truss faulting. So in truss faulting, the horizontal stress, the maximum horizontal stress is the greater stress in the crust, right? So it tends to displace the rock, like it pushes the rock upon the other one, right? And then the vertical stress is not the biggest one. And you have also the minimum horizontal stress. So in this case, the vertical stress is gonna be the lowest stress in the region. So, I mentioned this, fractures will grow perpendicular to the minimum horizontal stress. Why so? Well, you can think of, the fracture is an opening, right? So you crack open the fracture and then it tends to close in that direction, right? So they grow perpendicular to this stress, and the fracture height, the fracture propagation in the vertical direction is controlled by the closure stress, and more precisely by the difference between closure stresses or those minimum horizontal stresses, right? So in a normal faulting regime where the overburden is the highest stress, and then you have a maximum and minimum horizontal stresses. So you have something like this, right? So this example shows you what the stresses are or how they look like more or less in the subsurface. And you see that there is a high stress here, right? And then you have low stresses in this area all the way to here, more or less, right? And when if you were to apply a fracturing job over here, this is how the fracture would look like, right? So it will grow in this region of that has low closure stress, right? And then you will also have a little bit of vertical fracture growth right here because of the low stresses. So fracturing will grow, I mean, the fractures will propagate and grow both laterally and vertically until it finds this stress barrier, right? And remember the concept we talked earlier about stress barriers, the two things containing the fracture. This is what happens. So this is to tell you guys that fractures will also grow in non-productive regions, non-productive basins. And the only thing that can stop the fracture growth is the stress contrasts, or the difference between stresses in the different formations. Here's a map of how stresses look like in Texas, for instance. So it is really, to me, it's very, thrilling, exciting to see that Texas has a lot of changes in in its stress regimes. So look at this. We have different ways in which stresses kind of orientate themselves across the state. For instance, if we look at the Eagle Ford over here in this area, if you remember, the Eagle Ford is mostly normal faulting regime that you will encounter over there. So that you know that the vertical, the overburden stress is the highest, and you have two different horizontal stresses, a maximum and a minimum. Then the fracture will open against the minimum horizontal stress. Then we have Barnett Shale. So Barnett Shale is, according to this scale, is more or less in between strike slip and normal faulting. So you can picture that fracturing this region might be a little bit trickier because you gotta be a little bit more mindful about the stresses in the area, right? Same here, it's it's like in northern part of Texas, we experience a strike slip stress regime. So things get a little bit messier over here. And as you can expect, you don't see much of fracking activity over here, not over here, like here in the Permian Basin. And finally, in Oklahoma, you get a strike slip and a little bit of reverse faulting. But contrary to this area, you have a lot of fracturing activity or fracking activity going on in the scoop and stack formations in southern Oklahoma. It's a very, very prolific region. But in Oklahoma, they also have the issues with induced seismicity, which is worth another webinar. Is a very, very interesting topic about how the fluid finds its way in the subsurface to go through faults and reactivate them. So fracture propagation models, this is basically a description. This is how people back in the days tend to model fractures, because is the subsurface, you don't see what's happening, and you want to at least have a very, very rough understanding or idea about what's happening in the subsurface, right? What's going on? What happens if I vary this property, if I change viscosity, if I put more or less propellant? So back in the 60s, people created a couple of very interesting models. They were both based on this slit model. It's an elliptic crack model that was proposed by Sneddon back in the 1940s. And these are two different models. I'm gonna talk a little bit about both of them. So we have here the PKN model, which is this one, Perkins and Kern. It was later modified by Nordgren. And we have the Gersma and the Clerc model, which is also sometimes called the KGD model. I think that's the most popular way to call this model, the KGD. And in both models, one of the biggest assumptions is that the fractures are vertically confined, so that there is no vertical fracture growth. And this is showing how the conceptual design of these fractures go. So PKN models typically are just long fractures. You can think of them as the fracture length. Excuse me, fracture length is much higher than larger than the fracture height. But in reality, you will have this type of vertical fracture growth because fractures are too long that it's very difficult to keep them contained within the target formation. How much fracture will grow vertically? It really depends on the stress contrast, but they can grow very largely. Sometimes they just grow a tiny bit, like over here. Like you can think of this like, yeah, we got this vertical growth when we are fracturing, but as soon as we stop putting fluid into the fracture, then pressure is released, and then the stresses will tend to close this up here and same here in this direction. Sorry about my drawings, not the best. But the idea is that those fractures, because this region over here is supposedly higher in stress than the target formation, it tends to heal itself. That's the whole idea. And then on the other hand, we have KGD fractures, but KGD are tall fractures. So in KGD fractures, or contrary to PKN, which are long fractures, KGD are tall fractures. So when you do like frac packs, you can think of KGD fractures. And this is more or less the conceptual geometry, how it was developed. About the difference between the two, one to apply one to apply the other, it really depends on where you are at during the fracturing process. If you want to think about how fracture grows as we fracture the formation, it goes something like this. So this plot, I like this plot because it compares the models that I just showed you, these two. I forgot to mention the radial model. The radial model is essentially one of these. It's like this one, like the KGD, but the difference is that the height is going to be equal to this half length. So you will have a half of a half length. So you have that penny shape type of fractures. But then when you start, fracturing your well, you can think of like, you get the KGD or GDK model, right? The tall fracture. So it's a tall wellbore with a tiny fracture, right? So it begins to grow until the radial model hits up. So the half length is equal to half of the height. So it's radial, and then it goes past that region, and then it becomes longer and longer, so that the PKM model is more appropriate. So essentially, this plot is telling you which directions fracture would grow. And of course, this model applies to certain cases, and believe me, it's being used. I myself use the 2D models very often because there are formations that let you use it when fracture jobs are not as massive, or are more concentrated in a region that has good stress contrast between the formation layers. Yeah, a 2D model can do the job for you. But we also have 3D models. But before getting into the big one, let me mention about the pseudo 3D models. So, people quickly found in the 70s, 80s that the 2D models don't apply for a certain situations, particularly in heavily layered formations where you have really wild changes in the in situ stresses. So how do you calculate or estimate fracture dimensions, like fracture half length? It's very mind-blowing to think about it, because you can't really see from a modeling perspective how fractures will grow in such a variable environment, right? So it's not, these pseudo 3D models are not as straightforward as the 2D models, but they are very useful because they allow for vertical fracture growth. And here's an example of those. Here's the formation. Assume that this is the pay thickness of your formation of interest, and then we have these contrasts in stresses. And you can see that the higher stresses above and below the thickness, the formation of interest, are S6 and S1. So you would expect your fracture to grow until it finds those tops, right? Those limits, those stresses. So that, this is more or less what your fracture is going to look like after a while. And interestingly, this is your gross interval. This is the interval you are interested in. So the fracture grew until it found the stress contrasts. But then what do we do with this, right? It can be a little tricky because, these formations can be water-bearing formations or aquifers or aquithards or gas formations you really don't want to produce because, gas will move faster than oil, and then your oil production will go down. There are several reasons why you don't want this to happen. And of course, fluid leakage is another concern, right? Like the fluids leaking up to the subsurface, to the surface through vertical fracture growth is very much of concern to water pollution and stuff. But for engineering purposes, we are putting a lot of horsepower, a lot of propellant, a lot of fracturing fluid into regions that perhaps will not contribute to productivity. Therefore, basically, that's money waste. Full 3D models, well, as the name implies, very accurate, is the big deal, is the precise way to estimate fracture dimensions. So they give you a more realistic estimate of, as I say, the fracture geometry, which can lead, and of course, to better designs, better wells, better results. But really, the key to any model, be it the 3D or the pseudo 3D that we just reviewed, is to have a complete and accurate description of the subsurface, right? Like, as long as you have an accurate description of how stresses, what is the stress profile in the subsurface, you will be able to decide whether or not a pseudo 3D, a 3D, or even a 2D model will fit your needs, right? Most cases, I got this from the literature, most cases, you should have information on about 5 to 25 layers of rock, that will possibly affect fracture growth. So you can think of 5 layers above, 5 layers below, or 10 layers above, 10 layers below, the target formation, for you to kind of come up with a good understanding as to what's happening when you're fracturing this well. So it is, as I mentioned, it's better to enter data on as many layers as feasible as possible, and let the model determine the fracture, the vertical fracture growth as a function of where the fracture is started in the model. So they are very computationally expensive. Typically, you use finite element modeling for these simulations, and but the cost is worthwhile, in my opinion. So it will give you really unique insights of what's happening down in the subsurface, particularly when you have a stack base, like you have different reservoirs stacked onto each other. So the fractures can grow in many places. So it is of your interest to at least have an understanding of what is it happening, why or how is it happening. Example of it, some examples are here. You see you have a full 3D fracture model that shows you how fractures will grow in a multi-frac well. Think of this as a fracture stage, which has 4 different sets of perforations along that short lateral length. So, you can imagine this as being a well like this. And this is a stage. You have a plug here. You have another plug here. And we also talk about this in a minute. And then you have a set of perforations here, another set of perforations here, here, and here. They are typically spaced. And then you pump your fracturing job, right? You pump your job, and then your question is, well, how will fractures grow in this case? Where are they going to go? And as you can see, they are not symmetric. You might think of, oh yeah, I know everything is symmetric down here. So if I inject a certain amount and I calculate losses by friction, losses by, viscous effects near or deep into the wellbore, but the reality is that when fractures grow, they will compete with one another, right? Like which is stronger, which is gonna grow the most. So that's why you see kind of these external fractures that you see over here pushing this up. It's amazing. This is called stress shadowing effect. That the fact that you have multiple fractures tending to grow in the same formation at the same time creates a lot of compression. A lot of compression is created around the fractures so that they tend to close, right? They tend to push one another, and laterally speaking, and then stresses become distorted. You cannot see all of that with a 3D modeling. And over here, this is a very nice example. I like this a lot because it showed you that, you started your fracturing job here. This is your formation of interest. I will assume that this is the net pay that you want to stimulate, right, to fracture. But then look where the fracture grew, where it went. So probably most production, if there is any, will come from this region, right? So if this is an aquifer or an aquitard or a water bearing formation, so you will have problems because there's a lot of water that's gonna come from the upper formation. This is an example of an ice fracture, very well contained. And again, same example here. Fractures grow wherever they want. I heard this saying very often. Fractures grow wherever they want. But all of this is possible for you to capture using a full 3D model. Now, what you might wonder, what's the difference between pseudo 3D and a 3D model if you have a decent variation in vertical stresses, in the minimum horizontal stresses. So you see here, this is your target zone. This is where you create your perfs. And this is how the fracture is gonna grow according to the pseudo 3D model. But when you run the 3D model, this is what you get. So you don't have, in this case, you can actually call this a KGD fracture, right? Because it's a tall fracture. But this one is a PKM fracture. And this is more accurate in the sense that it captures what happens with this barrier here, with this barrier here, and with this barrier over here, right? And in fact, you don't have any barrier because the stress grading is more or less uniform. So what the message here is that they all, although they serve the same purpose, which is letting you understand that production driver, which is fractures or completion simulation efficiency, you may want to decide which one is best for you, okay? Depending upon the situation. Lastly, for this section, I have this one. So this is the treatment design. We have different parameters from which we use to design the fracturing job, right? We have fracturing fluid properties. We talk about viscosity of the fluid, whether it's Newtonian, non-Newtonian, if we're gonna use slick water, if we're gonna use some type of cross-linker so that the viscosity will degrade over time when it encounters temperature. If you know the temperature of the reservoir, you will design your fluid so that at a certain temperature, after a certain time, your viscosity will lower so that you can flow grow your fractures with little viscosity. So that's something you do in the fracturing fluid properties design aspect. You also have the mechanical properties, not only of the subsurface, but also of your mechanical equipment, right? So you have, you must calculate how much horsepower you need to create those fractures, right? And that will tell you who to hire, which company to hire, right? Like the one that has the biggest truck, or you just need moderate pumps to create, to perform the job. and also the size in terms of volume. How much fluid are you going to put down there? How much fluid do you expect to get lost during the job, right? Because once you create the fluid, if there is any permeability, because there is permeability down there, fluids will tend to, invade imbibe into the formation. So we gotta be careful about which fluids to use, not to not lower the relative permeability of the hydrocarbons in the in the surface, in the fracture surface area. We gotta be very mindful about it. And also injection rate. How fast do you want to grow the fractures? Some people, there's all sort of arguments. I've been to, excuse me, I've been to several conferences, and people say like, oh, a typical range will be 20 barrels per minute per cluster, or 30 barrels per minute per cluster, but it's really a number. And it comes from experience. For you, it might work 30 barrels per minute in a certain information that you know very well, and on average you've seen that that's a good number, but that number doesn't necessarily apply to a different information. So just start in that duality that, well, okay, how fast do I pump? Should I pump my fluid? So for those matters, you need even the simple 2D model can do it for you, can give you a very, very broad and really nice insight of the effect of fluid volume and pumping rates into the fracture shape, the final fracture dimensions. Overall, these are the properties or the factors influencing fracturing in your reservoir. Fracture height, we just did an extensive review on it. You have Young's modulus. This is new in our talk today. So Young's modulus is the how do you call it? Is the elasticity modulus. We used to call it often known as E. Is basically I'm going to show you, is basically coming from this concept. So Young's modulus is that slope between strain and stresses. In other words, how much stress you need to apply in order to deform the rock by a certain amount, right? So the different regions in the strain stress plot is that this is what we call the linear region, right? Up to this point, this point is typically called known as yield point, right? SY. If you look at mechanical like pipes, this is what they call the SY is the point beyond which, or the stress beyond which your material will deform plastically, meaning that it will not recover its original state. Over here on this, during this linear type of behavior of your material will basically behave like a spring, right? So I'm sorry about it. So the material will deform, and the deformation is indicated by this, depending upon how stiff, right? How stiff it is. And then that stiffness, if you will, is dictated by the Young's modulus. So this is the equation for the linear region. And there is another very interesting insight over here. I'm sorry. There is another interesting insight over here, which is, in your opinion, can anybody tell me which rock is preferable to have in a reservoir? Is it rock A or rock B? I'm gonna answer. I'm gonna answer as we talk. So you would prefer to have a rock that fails. Which one? Okay, I'm gonna assume that Motrek say A. So rock A, that's correct. We would prefer a rock that will not absorb a lot of the energy that we're putting into the fracture, right? Because if you are injecting fluids, you don't want the rock to deform. You want it to crack, right? So if you have a low Young's modulus, if Young's modulus is low, then your rock is gonna is gonna stretch. You can think of the spring, of that spring is gonna stretch. And if you just unleash it, you release it, it will just go back to its original state. So you have to put a lot of energy. And in fact, I think that if you integrate this area, you will get energy density, if I'm not mistaken, from my mechanical engineering days. So think about the crazy amount of energy that you have to put in order to crack the rock, right? And also because its ability or you know, the rock tends to go back to its original state, even though you frack the rock, but the rock around it doesn't. So it will tend to close faster. So you will see a lot of geomechanics effects happening with rocks of this type. Whereas rocks of type A, they will, you put energy, but all that energy is being utilized towards reaching the yield point to later crack the rock very easily, right? So you don't need a lot of deformation for these rocks to crack. So these are preferables. All right, so that's what I wanted to comment on Young's modulus, why it's important. So remember, you will always like to have a high Young's modulus and a low Poisson ratio. So Poisson ratio also has to do with deformation, but I don't wanna extend myself in that area. Fluid losses, important parameter also. I touched briefly about it in the previous slide. So fluid loss is basically how much of the fluid that you're putting into your fractures are going into the formation, are being lost to the formation, right? So you might want to control those losses, namely Carter losses and sport losses. That's what they are called. So this is another very important parameter. Now, fracture toughness. Fracture toughness speaks about the resistance of the rock to let the fracture grow, right? So the higher the toughness, the more difficult it will be to propagate the fracture. But interestingly, stresses at the tip of a fracture are theoretically infinite. So a fracture will grow definitely, but how hard you have to work the fracture depends on the fracture toughness as well. And finally, we have two components that are more related to the fluids. Fluid viscosity are really, really important component because that viscosity is what's gonna, is gonna impose or put that shearing force into the fractures, right? So you have that shearing effect that will help you grow your fractures. And lastly, we have pump rates. How fast you do this is gonna be very, very important and decisive when you go to create or to design your fracturing job. All right, so that's what I got for the fundamentals on hydraulic fracturing. We're gonna jump here into another topic. So perhaps Wate, correct me if I'm wrong. It's 9:30 here, so it's 5:30 local time. So do you want us to stop for the half an hour break or whichever way you like?
Yeah, I think it's better to take a break now, 30 minutes.
Okay. A little bit about the fundamentals of hydraulic fracturing.
Oscar, do you hear me?
Conventional wells.
Can I talk?
I can hear you.
Okay. First of all, thank you very much for this lecture. It was really
Yes, sir.
interesting. The unconventional wheels is always very interesting from most of the engineers here in Iraq.
Yes, sir.
And if I may ask, what you think, what is need for the Iraqi engineers here in Iraq, especially in the south and in Basra, to starting thinking seriously and bringing the needs or the required tools to starting the unconventional wheels design for our oil and gas area, actually.
Yeah.
By the way, this is Chief Engineer Firas from Basra Gas Company. Thank you.
Yeah, that's a very good question and a very valid point. I think if you want me to tell you all my personal experience, It's a journey. It's a change in gears. We can talk more about it at the end of the QA session. But yeah, this is what I'm trying to do with this presentation. This is what I'm trying to accomplish, by the way. So I'm taking you guys little by little from the conventional world to the unconventional, so that you kind of have a better glimpse as to what are the difference, why are they different, right? Because many people talk about, yeah, they are different, but the difference in the end are not very well known by them, right? So the more we talk about the fundamentals of hydraulic fracturing, how they work in conventional reservoirs, what are the real implications, right? The parameters that affect the hydraulic fracturing, like fracture growth, all of the models, and how do they ultimately would affect recovery was not covered in the previous section. That's what I'm going to cover here. So this is a reality check. This is sometimes I look at these pictures just to get back on earth. Sometimes I go on my imagination and thinking, oh yeah, this is very good, this is fantastic, if we can do this model, that model is going to work. Yeah, but on paper, this reality, what I call here again a reality check, is that rocks are not as isotropic or as homogeneous as we think of them. Here, this one I love. This is an example of the Eagle Ford group. In the Eagle Ford, we have two different formations, productive formations, the lower Eagle Ford and the upper Eagle Ford. At the end of the presentation, I'm going to show you a field example with this lower Eagle Ford formation, how to identify the production drivers over here. But here's the Permian Basin. I personally went to this trip. It was almost 2 years ago. It was a very, very interesting to note all of these formations. Like, look at this, how fractured this formation is, right? So imagine creating a multi-stage fracturing in these formations. How will fracture grow, right? Where they will go and how will they look like production-wise. There are two completion techniques. There are two main completion techniques in unconventional reservoirs, namely plug and perf, the one over here. This is by far the most common, and we have the pinpoint frac slip. It's commonly known as frac slips, okay? What they do is basically, or essentially the same, creating multiple fractures. They do have, different applications though. To begin with, plug and perf, sometimes called as PNP, is the most common completion technology. Why is it the most sophisticated? No. Is it the cheapest? Yes. So for economics reasons, plug and perf has permeated in every unconventional basin you can think of. Even in South America, Argentina, which we have Vaca Muerta over there, you find plug and perf completions. So what is the overall, design behind plug and perf? Basically, you have plugs, or you plug your horizontal well in different areas or different locations along the lateral, and you begin with the toe of the well. This is the toe, and this is the heel. Okay, so begin with the toe of the well. We place a plug. We isolate this section, which we call stage 1, right? And then we create different gunshots. We create perforations. Remember I showed you this earlier? We create different perforations, and the number of them, it really depends on the tool you use to shot, or how many shots you have available for this completion. And then you pump your fluid, right? And then fluid pressure will grow here, and then you will get your fractures initiated, which Ahmed asked the question, very interesting question, and then you grow your fractures. This is more or less how it goes. And then you seal this, and then do the same here and here and here. So controlling flow rate is key. Why so? You have different perforations or set of perforations with equal number of perfs. So you can imagine that you will, if that's the case, if all of the perforations are equally the same, have the same geometry and all, flow will tend to grow with fracture, the one that is the closest, right? And then you will get unequal fracture growth. So you will hear about partial penetration or limited entry perfs. That's what they mean. Basically, they seal um, different holes in order for, for the fluid to distribute better within a stage. So that's how you create the different stages. And to Ahmed's question again, fracture initiation and propagation is really uncertain. Uh, it really depends, but typically fractures will initiate at the weakest point around the wellbore. That weakest point, well, unless you have borehole data like borehole image data, you will not know. It's highly uncertain. But once the fractures, crack the rock, like for instance, you can typically assume that you will get one fracture per cluster. So even if you have many holes over here, you create one fracture, and then once that little crack is created, all the fluid will go there, because that's the path of least resistance. So if you have a stage, this is a stage, remember, this is what we call a stage. If you have a stage with 4 clusters, this is what we call clusters, okay? These are clusters of perforations, or perforation clusters. So you will likely have one dominant fracture per cluster, and sometimes per stage. When these clusters are too tightly spaced, you could have created different fractures, but there is this one fracture that's gonna overgrow the others. So you will have a tiny fracture over here, but then the other one is that will overgrow the other fractures, right? Because they are competing with one another. So now the problem becomes a little bit tricky, right? Like when we compare these against the conventional environment in which we have one fracture, our problem was the vertical growth. Here we have multiple problems, including vertical growth. Let's not forget about it. We still have the problem of vertical growth over here. And on the other hand, we have the frag sleeves. Frag sleeves is an advanced completion technique. It really, to me, is the best completion technique. You have one sleeve with the perforations already created. So it's basically you manufacture this sleeve, and it has very high technology. How you close it, how you seal it. It can be coil tubing activated. It can be ball activated. It can be wet line activated. There are several ways in which you can open these ports. That's what they're called, ports. And then you seal them by dropping a ball, right, to go to the second port, and then you seal it with a ball. And typically these balls are magnesium based, or materials that have manganesium, sorry, so that they dissolve at a certain temperature after a certain time. Or you simply lower your drill, and then you drill out these balls. That's more or less how it goes with frag sleeves. What are the advantages? Well, it's evident that you can control where your fractures grow, right? Because you know that you will have one fracture per sleeve. So, and again, as a reservoir engineer, that's my dream, because I know what I know what I'm doing with just one fracture instead of trying to control 5 at once. I mean, in fact, here in the US, I have heard of even 10 clusters per stage. On a stage, typically this spacing is about 100 to 100 feet. In the first generation wells, the spacing was around 300 feet, which is about 100 meters, more or less. So controlling fractures growth, simultaneous fracture growth, can be tricky over there, but not here, because you have one fracture, and then you can do whatever you want with it. So you know where the fracture is going to initiate, because there's no other point where fracture is going to go. And of course, you will have more control about what's happening around the fracture, right? Because you have just a single fracture to take care of, then you will know what to do. And of course, the only drawback to this is that it's very expensive. Performance-wise, whether this technique is better than plug and perf, I have seen papers, particularly from the Marcellus, in which frag sleeves, make a difference when compared to plug and perf. but not as substantial. And I've seen other wells. I personally see them in the backend, from which, you know, the frac slips have made a significant improvement to well productivity compared to plug and perf. But again, it really depends on your budget. How much money do you have? You have to, you know, to invest in your completion, and how difficult it is to complete your well in the specific location that you are um, um, working on. So, you know, I think I gave you a sense of what are the challenges here. At first glimpse, we have a long lateral section. So here, I mean, in the past slide, we saw 4 sections, perhaps 4 stages, but in long laterals, actually, you will have 30, 40, 60 stages. So controlling these problems become more difficult. And horizontal sections, as I said, they range, I mean, from 4,000 feet to all the way to 2 miles, which is 2.2 kilometers. So when drilling such long wells, you know, staying in sun, when you're drilling, staying in sun often becomes difficult. And it's logical that if you don't have a good control of your geosteering process, well, it will be very difficult for you to, you know, to land your well and keep in the target formation. So that requires, I mean, for you to drill those wells and staying in sun, particularly, or geosteering in unconventionals, you know, you have to rely on you know, geochemistry. You have to rely on logs, so that, you know, you can make the adjustments to the bit as needed. That's what we call the geosteering. Now, given the long distance, on the other hand, given the long distance on these wells, you know, we have a lot of tortuosity, we have a lot of heterogeneities. So you can imagine how heterogeneous the rock can be. A rock that spans kilometers can be, right? So you will expect some things to change along the lateral. So here, this plot shows you more or less what I mean by that. So let's assume, or let's suppose that here, this one is the target zone, right? So this is your planned well trajectory. So in plans, your well is nicely landing on the target formation and then going all the way to TD, right? So here you have the true depth, I mean, MD, that's where the toe of your well is, that's TD. But then in reality, you encounter all sorts of troubles when drilling your well, right? So for one reason or another, you know, you have rock variability here, over here, over here. You found a hard strike over here, and then you're be deviated, and then you drill out of zone, you come back into zone, and then all right, you get there. You made it to the end, right? And then how to complete the well, that becomes a challenge, right? Because drilling engineers sometimes, and I had this discussion very often, like drilling engineers are really worried about drilling the well the fastest, right? So they can, you know, boast, oh, I drilled this well in 7 days. And then they throw it up to to completion guys, and the guys that just scratch their heads and like, what am I gonna do with this well, right? Because now the completion phase becomes challenging. So you have some fractures that will stay, that will stay in sun, right? But then others that perhaps you don't even want to frack. So you can actually forget about this. You can forget about this fracture. Well, not this one, but then what you had, you know, design is not what you got in reality, right? So the productivity of your well, is not what you would expect. So your performance driver, your completion performance driver here is heavily affected by drilling and completion itself, right? So this is the message here. So staying in zone is critical in order to access all that the reservoir has to offer. This is fundamental. And again, here in particular, here in our company, we use what we call engineer completions. So engineer completions is basically the use of real-time data, geochemistry data, and logs in order to see where we are at down here in the subsurface, so that we can geosteer using artificial intelligence and machine learning, so that the computer tells us, hey, according to this data that you gave me, you will probably want to, adjust your bid a little bit because there is a change in something, or there is going to be a change in this property or an MSC or whatever the case. This is what we call look ahead capabilities, right? And that's I think that's a topic for another discussion, but machine learning and artificial intelligence can really help over here. Here's another example, same deal. Here I'm showing the instantaneous shut-in pressure. This is what it's called. Basically, this is the pressure that you get back when you fracture your well. So let me try to plot this. So this is time, and this is the injection pressure or pressure downhole. So you initiate your, you start your pressure job, your fracking job, until you boom. Remember, you reach the fracturing point in which you crack the rock. That's the failure point. And then your pressure will drop like this. Well, not like this, a little bit more smoothly, like that. And then this pressure is the pressure that you get instantaneously after you stop pumping, okay? So this pressure over here is called instantaneous shut-in pressure. And then this pressure is telling you something about the formation, right? So if the formation is isotropic, or at least homogeneous and uniform, you would expect a similar ISP along the lateral, right? But look at this one. So your ISIP will vary from anywhere from 3,000 PSI, right? All the way to past 6,000. So it's a huge variability, right? So this is telling you that, well, you may have different rock types along the lateral. So when you design your completion for this multi-fracture well, be mindful about it, because the completion requirement for stages like this, for instance, like this one that have, these ones that have high ISIP might be different from this, right? So you have different rock types, and here at our company we have artificial intelligence algorithms that will cache this up, and then will tell you which is the best way to go for a particular rock type. Now let us get into the stimulated reservoir volume. What is this concept? What do I mean by that? Earlier we talked about how do we initiate a fracture in a vertical well. Now here in a horizontal well is going to be more or less the same. Here I'm showing one cluster. You might have other clusters over here, but now at this point I'm focusing on this one cluster. Now, and again, we will assume that one fracture is going to grow out and it's going to be dominant per cluster. So you have this fracture growing out as you inject. You initiate your fracture, and then your fracture is going to grow. So you get fracture propagation. So fracture is going to propagate, right? It's going to go this way, this way. However, you are going to start seeing these things, right? You will have what is known as fracture branching. So you will have a lot of branches happening outwards. And this is really what you want, right? Because remember what we talked earlier, we want to, stimulate our near wellbore area as much as we can, because most of the production will be coming from this region. So in the end, your fracturing job will look like this. So ideally, you will want to use some sort of technique to, screen out the fracture grow laterally. So you might use far field diverters. I don't know if I pronounce it right. You write it down like this: diverter. So basically what this does is they screen out the tip of the fracture so that whatever fluid you put into the fractures is gonna grow. It's gonna go in these directions. So the good and the bad. The good is that you create a lot of fracture complexity around the hydraulic fracture so that you can access all of these resources stored in this region, right? And that's what we call as stimulated reservoir volume or rock volume. So it's this volume over here, right? So if you can contain this volume and extend it for other, let's say if you have another cluster here, so you have another rock volume here, a simulated rock volume. So essentially you are accessing a lot of rock, right? You're accessing a lot of fluids in the reservoir. And again, I cannot emphasize this more, but all of the production of your well will be coming from this region, okay? So this is what we call a stimulated reservoir volume. So why is the need for coming up with this definition? Is because I mean, if you connect what we talked earlier about planar fractures with what we're talking here about fractures competing with one another, growing in the same location. So the concept of a planar fracture and its conductivity are insufficient, really. You cannot describe a fracture stage in a multi-fracture horizontal well just using these two concepts. You need more. And it's mainly because of this fracture complexity happening around the wellbore, right? So you have this fracture grow, but then I think the challenge here is, well, how do we represent it? How do we mathematically, how do we, empirically say, hey, this is how much of stimulation I got from this well, or this is how much stimulation I'm gonna get out of it so that, production is gonna look like this and that. Is really difficult. So we call this the SRB, and the way we define the SRB is using a technique called microseismic clouds. I'm gonna show you next. So basically that describes the microseismic cloud describes or shows you all of the locations where seismic activity had occurred while you were fracking your well. So in other words, when the more dense that cloud is, the more stimulation you got. That's the concept behind it. And of course, that amount of SRB, that amount of stimulation around the fracture stage will tell you or will correlate somehow with well performance, right? The better the stimulation go, the better the SRB quality, the better the production performance or expected production performance will be, right? A couple of plots showing what I meant with microseismic clouds. Essentially, you have two different fracture wells. I like this image a lot. It's very descriptive. So you have two horizontals from the same path. And by the way, that's what you call a multi-well path. So basically you have a path on surface with different wells, and they look like this, okay? They typically go this way. You have like this well going in opposite direction. Does anybody want to guess why? Well, okay, so I'm gonna give you a clue. This one, we say that fractures will grow perpendicular to which direction? We say to which stress. So we say that they grow perpendicular to the minimum horizontal stress, right? And along the maximum horizontal stress. So if you know where, remember the map that I showed you about Texas the state of stress in Texas, this is what it is for. So if you know this direction, you will land your wells like this, and then your fractures, you will expect your fractures to grow like this. Okay, sorry, this is the max and this is the minimum. Yeah, this is the minimum. Sorry about that. This is the minimum and this is the maximum. But you get the idea, right? So this is how it goes, more or less. And again, this is what you call a multi-well path. You will hear that term a lot as well. And so this is what the plot on to your right is showing on the right hand, right here. This is a multi-well path, but it's only showing two wells, okay? So they have, you can perceive it over here. They have a monitoring well, is typically a vertical well. that has geophones in it right here. So you see these dots, small dots over here, those are geophones. So geophones basically record your seismic activity as you will do for any other application. And this is the microseismic cloud. This is how it happens. So you see all of these events, and then over here, they are showing you the stages or perhaps the clusters, right? And then the fractures, what seismic activity you got from the fracturing process. Here's even more detail. It's the same concept, but then the coloring shows you or indicates the stage that you're looking at, right? So coloring basically is telling you which stage you stimulated and how that stimulation went for that stage. So this is, you can call it, this is one stage, the yellow one, and you get the green stage. And just by merely looking at it, you can see that some stages did better than others, right? So this is the whole purpose of the microseismic cloud. Now, there is another concept we need to be aware of, is this. So SRB is, how well your simulation went, but now we have drain rock volume. So what is the actual fluid or region that I'm accessing with my simulation? So how far depletion reaches is essentially the drain rock volume. So it's essentially, you can think of this as the pressure wave that I showed you in the first slice, spreading out. So that's what this plot is showing you, right? How the pressure spreads out around a fracture. Therefore, you are accessing these volumes. And again, if you think about the conventional wells where we say, hey, we have a tank with a fixed volume that we're draining from, you can think of this as a dynamic tank. Therefore, the drain rock volume is a dynamic concept in nature, in a sense, right? It's definitely different than the SRB, or it might be. It really depends on the permeability. So if let's say, for example, this entire rectangle here is the SRB, okay? Let's assume that it is the SRB, and that SRB has a certain permeability, right? So long as the pressure difference between the pressure at the wellbore, right, the pressure, and the pressure here is high enough to drive fluids out of it, you will expect that the drain rock volume at some point will be equal to the SRB. Otherwise, it will not reach the boundary. So you will see transient flow going all the way through, even through the SRB region. Another thing that can impact these these drain rock volumes is a fracture-driven interaction. So basically, if you have two wells, even from different paths, let's say that you have another path over here, right? You have another path, and then you have one path here, and then you have fractures, right? If you create this fracture, I mean, if this is a new well and then the fracture do this, or the fracture do this, then, you intersect fractures from wells, you can expect that this drain rock volume will reach that well as well, right? So this phenomena is commonly known as frac hits. I published several papers on the topic. But basically, essentially, you will know that your productivity from the older well will drop. This one will momentarily go back up, but in the long run, this will be behind frac hits. Okay, let me take a look at the chat before we move onward. Okay, all good. So closure stress and pressure. We talk about the minimum horizontal stress, right? It's typically represented by sigma and small h. Just to say, is the smallest stress in the horizontal direction. You will find this formula, this equation, more often than not in the books, in geomechanics books. It says that the minimum horizontal stress in a normal faulting regime, Remember, normal faulting, the vertical stress is the overburden stress is the highest, and then there is a maximum and minimum horizontal stresses. So the minimum horizontal stress is proportional to the difference between the overburden and the pore pressure. But note that that pore pressure is being modified by Biot's coefficient, right? So for now, let us assume that this is just a constant, more or less equal to 1, plus this pressure. So, if you subtract pressure from here, then this becomes an effective stress. But interestingly, you have this term over here. This is related to tectonic stresses. Normally, you ignore them because there's not much, typically it's not much tectonic stresses in the areas of interest. Now, when you are on an isotropic stress regime, which is the worst, let me tell you, what do I mean by isotropic? Isotropic means that the horizontal, minimum horizontal, and maximum horizontal stresses are equal or nearly equal. That's a mess. That's a headache, because imagine, remember we talked that fractures grow along this direction and open up against the minimum horizontal stress. Well, guess what? When these two are equal, where is the fracture growing? How are they opening up? So it becomes a headache. But for that case, this K over here, it can be represented using the Poisson ratio. So we have this number here is the Poisson ratio, or I don't know if I'm pronouncing it correctly, but it's Poisson's ratio, okay? And so that ratio tells you how deformable is the rock, but this is the way you calculate it. Interestingly, this plot over here tells you that the changes in horizontal, minimum horizontal stress are related to changes in pressure by an approximate amount of this, right? This is more or less a good approximation. But what is interesting about this is that this is telling you that changes in minimum horizontal stress are really proportional to changes in pressure, right? So if you have a lot of geomechanic, properties that depend a lot on stress, as we're going to look next, and fracture conductivity, for instance, is one of those, then you can represent stress-dependent properties as pressure-dependent properties, right? As long as you have the right correlation. Porosity and permeability more often than not depend on pore pressure, particularly in unconventionals. You will hear a lot about pressure-dependent permeability, and porosity, and all that stuff is because they do highly depend on pressure for the very reason that they naturally or intrinsically depend on stresses. And well, that's one main difference with conventional reservoirs, right? Because we often assume in conventionals that permeability is more or less constant. We often say it's a constant value. Perhaps it's not a good, sometimes it is, sometimes it's not a good assumption in unconventional reservoirs. Fracture conductivity, this is the capacity of the fracture to drive fluids through it, within it, right? It's defined as the product of fracture permeability times fracture width. So this concept is very simple. This is the way you measure it. At least here in the States, or here in North America, the units of measurement for it is millidarcy per foot. Millidarcy foot. Low conductive fractures will be in the range of just a few to 20 millidarcy foot. And high conductive fractures will be anything beyond 500 millidarcy foot. Okay, just for you to have a number in your head. But again, these fractures, they are cracks. They are open cracks that, when you apply a certain amount of stress to them, a confining stress, they will tend to close, right? Because you're basically pushing the fracture back to where it used to be, an uniform rock, and you fill it up with propant, right? So what you have in here is propant that keeps the fracture open against those stresses. And if you're in the lab, or this is how vendors do it, and then they put some fluid through the fracture at a constant rate, more or less constant rate. So they measure the pressure difference and, plot this conductivity, right? If you do Darcy's law, you will be able to this, plot this as a function of confinement stress, right? And as you can see, it changes. It really changes. And you can think of it as the harder you push the fractures to close down, the lower the fracture conductivity will be. And that makes sense, right? So this is what we call stress-dependent permeability. So what factors other than stress affect or influence conductivity? Well, we have propellant placement, that's a huge factor, and it has to do with gravity. So gravity is everywhere, we cannot escape it. So when we pump the propellants inside a fracture, they tend to settle, right? They tend to settle, and then you create these type of banks. And over here, you did not effectively prop your fracture, so that's a problem. And your fracture will look, if you model your fracture, it's gonna look like this. So your fracture, effective fracture half length, if you will. So fracture half length, effective, okay? Well, sorry about that. This is supposed to be an E, effective. This is more or less how it goes. Another factor that influences conductivity is its natural degradation with pressure and temperature. This is one really good paper from McDaniel back in the 80s. He showed, he ran several tests with prop at a certain place as a high closure stress and a test temperature. And then he measured the fracture conductivity or how much it was retained. This is percentage, right? So you start at 100% and you can go as little as below 10% the original fracture conductivity without even draining pressure, but just because of the closure stress crushing the propellants and also the temperature, right? Making them weaker. And as I mentioned, fracture pressure, closure stresses, they are related to one another. But here this plot is showing you that fracture conductivity is actually a function of that closure stress. But the takeaway from this chart, this plot over here, is that here these three lines or these three data sets show you the conductivity of a propped fracture, meaning that they have propellant within them or inside them. Whereas this fracture here does not have propellant. So the SRB, as I'm going to show you on the next slide, the SRB, once we create this branching, is likely unpropped or remains unpropped, right? So these are just open cracks which the pressure is holding open, right? Because it's really difficult to excuse me, to transport propellant from here, the main fracture, into these tiny cracks. So when when you get to the initial point where you have your initial permeability for these, the planar fracture or the main hydraulic fracture, and then you consider the SRB, so you give it some permeability, right? Which is obviously, not obviously, but is much better than the matrix permeability. And then you start draining your pressure, your fluids. So the permeability of the conductivity of the main fracture, you just saw it, is going to tend to decrease. So does the SRB permeability. But as you see, this conductivity, I should say, is the correct way to call it. The SRB conductivity will drop faster. Remember the last plot? It will drop faster because these are unpropped fractures. So those are things that we need to keep in mind. A common way to represent this variability is using an exponential pressure-dependent formulation, which basically tells you that the permeability as a function of pressure is equal to the initial permeability or whatever reference permeability you have, multiplied by an exponential function that depends on two factors. First one is the permeability modulus. So you can think of this as a permeability compressibility, if you will, something like that, right? Because compressibility, density for oils and porosity follows a similar type of formulation. And then here, this delta P, this is the pressure drawdown in a particular region. So pressure drop between the average pressure in the fracture and an initial pressure is different than the average pressure in the SRB versus the initial pressure, right? So they, in a sense, this formula is also proving that those variations would be different. Now, one thing is because the fractures, even if you have a really bad fracture with really bad conductivity, and if it's really pressure dependent, in the end, that conductivity is way better than the conductivity of those fractures in the SRB. Therefore, you can typically say that geomechanics will affect the SRB the most. And this is a statement from what I've seen. I saw that during my research, during my dissertation. So it's something that is still open for discussion. Okay, so we'll reach this point. We're gonna jump into our next topic. It's 10:45. I don't know, Watek, if you want a 5-minute break before we get into the next topic, or if we want to go, we'll go straight.
As you like.
I can go straight, no problem, but it's about the audience. What they like.
Yeah, I think it's better to continue.
Okay, let's move on. Now we talk about fracturing conventionals. Now the difficulties in fracturing in unconventionals, all of the challenges, is the effect of stresses on our completion job. Now we're going to talk about fluid, how fluid moves when the completion is done. Several topics we're going to cover. We're going to start with the fundamentals of rate transient analysis, which is the theory behind production forecasting, right? So if we get this right, chances are that we're going to get a good understanding of how the production drivers will ultimately affect our estimation of ultimate recovery or economical recovery from multifracture horizontal wells. There are a few theories I'm going to go through. In reality, it's just models. They are just models that shape what we have today in regards to reservoir engineering from the modeling perspective. Let us begin with rate transient analysis. What is rate transient analysis? Well, before telling you what it is, let me tell you that it's closely related to pressure transient analysis. Difference being the time frame that you're looking at. Equations, flow equations, and I'm going to show you right now, equations are the same. There was a very, very fundamental theory about this that enabled us to use, to talk about rate transient analysis, decline curves, type curves, etc. So, rate transient analysis really implies the analysis of production data over long periods of times, unlike or contrary to pressure transient, which requires a lot of pressure data for short periods of time, but with high resolution, so that we can capture what's going on at and around the well. Rate transient analysis sees more or less the same things, but on a, I would say, on a coarse way. On a more coarse way, it takes longer, because no matter how your frequency is, what frequency you have, you can have rate data every second, but in the long run, it will matter what you get after months or even years, right? So it is typically, or at its beginning, at its conception, constant bottom hole flowing pressure right here was assumed to develop these equations. Game changers, this guy is Arps, Fred Kovish, and Dr. Blasingame did a spectacular job, a stellar job in laying the grounds, the fundamentals for rate transient analysis. But it goes back to the 40s again. Very, very fundamental paper was published there by Van Everdinger and Hurst. You might have heard of him from aquifer modeling in conventionals. But they did a fantastic job. By the way, they used to work for Shell here in Houston. So they took a lot of equations into Laplace domain, and they found that the pressure solution is equivalent to the dimensionless pressure solution is equivalent to the dimensionless rate solution by this factor. So they are proportional to one another, inversely proportional to one another in the Laplace domain. So what this means was that, oh my God, so now you have this. There were plenty of these solutions available for pressure transient analysis, right? Because all that we deal with in pressure transient analysis is pressure. So there were plenty of pressure transient solutions available. So you basically were able to convert them to variable rate solutions with constant bottom hole pressure. But why is this? I mean, where this came from? Back in the 20s, people began to observe that production data like this or here, they more or less follow an exponential trend, if you will. Here's our data. I know that this graphic is not very clear, is a little bit older, but then, you know, people realize that, well, if you fit a curve, which is the dashed line in the background, right? So if you fit a curve through this data, you will probably be able to forecast how much you're going to produce, right? So you have produced for this long, but then you can extend this trend over a certain period, right? So you will get to see, oh, after 12 years, I'm gonna, you know, be at this point and I will have produced this much. And then this is the foundation, this was the foundation for ARPS relations. So you may be familiar with this decline curve analysis with ARPS. Basically, he collected a bunch of wells and then he saw some wells would fit using an exponential type of curve fit. And by the way, this axis is in logarithmic scale, so be aware of that. And then he also found that other wells would fit hyperbolic declines and others would fit harmonic declines. So in theory, he came up with this formula. This formula has covered them all, right? What do you have about it? It's very simple. You have your initial rate, you have a decline rate, which you initially don't know, and you also have a curve fitting parameter B. And actually, you will hear a lot about that B in the industry. Everybody talks about the B factor, the B factor. If B is 0, if B is 1, if B is between 0 and 1, like this. But it turns out that some guys are feeding production data from shales. I'm sorry, this is not supposed to be like this. I'm feeding production data from shales like this, using the B factors greater than 2, which to begin with violates this conceptual formula, right? Here's an example of what ARPS did, or what you can do with ARPS using this is a hyperbolic, I don't know what to call it, decline. But look, B factor again is greater than 1. So I'm not lying over here. It's greater than 1 and people get away with that. Of course, you can observe that you have a very, very nice fit. It's a really good fit. Here is the cumulative production. This one is cumulative production and this one is the decline rate. And you can see, you can't deny it's a really good fit. But one question is, what role does reservoir properties, play in these forecasts, right? What roles do they play? We don't know, because we are just fitting a curve with against a formula. So reservoir properties, you don't know about them. Unconventional reservoir, remember guys, they have a lot of properties and completion stuff involved in it, and simply ignoring it is a bit tricky, right? Is this the unique solution to the model? What if, my coworker will come up and say, hey, I fit this curve with this data. I think my data, my curve fit over here is best than yours because I'm more awesome than you. I don't know, he can say anything. But then he came up with this cumulative production curve. And of course, it's higher, right? So which one is right? Who knows, right? Because we only have data up to this point. Moreover, some more guy in a more realistic mood will come and say, hey, Oscar, I think this is a more realistic decline because I observed from our wells that such and such. So his decline curve is a little bit lower than that you will expect. Therefore, the decline is going to be, I mean, the cumulative production will also be lower, and the EUR, or the estimated ultimate recoveries, will be different. Now, which of these is right? That's the big question, right? Which one is the right solution? So to avoid that bias, to avoid that non-uniqueness, Fedkovich came up with type curves, which join together analytical solutions for conventional reservoirs flowing at constant bottom hole pressure with decline rates. So basically, whenever you see this B1, I think this one actually is going to be exponential, and it's going to be transient flow. Everything over here is under transient flow. So if you overlay your reservoir data, you will be able to, to determine reservoir dimensions. You will be able to determine skin factors, and that stuff that you will not be able to using material balance equation. Remember that in material balance, we had to wait until you see all of the, pressures, so all of the boundaries of the reservoir. Here, you can get away with it using Fedkovich type curves. But then we have then the empirical decline or ARPS curves over here. Now, this works very well for conventional reservoirs, for homogeneous reservoirs with constant thickness, single phase flow with small compressibility, and in bounded reservoirs flowing at constant pressure. So this is what you will typically see, and this is what I was telling you. Over here, this is the transient flow region, and here's the boundary dominated region. Therefore, you will be able to see when in time you transition from transient to boundary dominated. And moreover, you will often not see that Fedkovich type curves also have the cumulative or the dimensionless cumulative production, so that if you have the production, there will be another parameter that you can match with your type curves. Blasingame, on the other hand, he brought a couple of groundbreaking concepts. He brought a couple of groundbreaking concepts. First of all, he said, like, we never really have constant pressure or constant rate. That really doesn't happen at the reservoir level. So he came up with the pressure normalized rate, in which both of them can vary. Similarly, we have the rate normalized pressure, which I personally use a lot, and I'll show you guys in a minute, and with the material balance time. So this basically tells you that constant rate solutions and constant pressure solutions are equivalent to one another when you use this material balance time, which is nothing but the quotient or the ratio between cumulative production at a certain time divided by that time. I say, for example, you produce 100 barrels, 100 STB over, sorry, this is rate. Sorry about that. And a rate of, I'm gonna correct that on the slides. And then this is at this rate, so 10 barrels a day. Okay, so this gives you time, right? Because this goes away with this, and then they will give you an equivalent 10 days. Okay, so basically flowing at constant rate for 10 days or for a given amount of days is equivalent to have flown at constant pressure for these days. More or less, that's more or less how it goes. So it admits variable pressure conditions. This is what it looks like conceptually. This is the constant pressure solution over here. This is a log plot of Q and 1 over PD. This is constant rate solution. So when you apply material balance, or you integrate your rates over time and then calculate your material balance like this, time like over here, so you get this. Basically, you stretch this dash curve, and they now fit to one another, so solutions are equivalent. That enables the creations of many type curves, because the knowledge that you can use solutions that were previously available for pressure transient analysis, now with the purpose of constant pressure or variable pressure solutions, enables you to create type curves for fractured wells, right? So for instance, here's the type curves for a square reservoir with a fracture, with a well and a fracture. This is what it will look like depending on the conditions. Using a different approach, which is the integral derivative approach, and then for compound linear type curves, and we're going to talk about this later. So this is basically a multi-fracture horizontal wells. Remember, these are the fractures over here. Can you see them? These are the fractures, the horizontal well, and the white region that you see there is what it's called the SRP. Okay, so these are the type curves for those for this type of wells. One of the first models that came around was Wattenberger. He say, you know, do you guys remember this plot I showed you way back? So this plot is basically saying, you know, I know that this is happening. I will not care about what's happening at the matrix because really all of the production is coming from this region. So I'm going to take a look into that particular region, which is the SRB, right? So he came up with this model, and then he further assumed that the fracture is symmetric on both sides, and that its conductivity is theoretically infinite. Therefore, you don't have any pressure losses. Therefore, the fracture is the well itself, right? So if that's the case, you will expect to have just linear flow, right? It's simple. It's as simple as that. It's just linear flow because this is like a crack, really wide open, and then you have flow going this way, and this fracture will keep its infinite conductivity like forever. That's the model. So from there, you generate type curves, or I mean, not Wattenberger generated type curves, and this is what they look like. This is, and remember, this can be PWD or this can be rate normalized pressure, and then this will be normalized material balance. So when you have the half slope here at early time is because you have this transient linear flow. Remember, transient linear flow is proportional to square root of time or material balance time. And then you have the unit slope, which indicates boundary dominated flow, because now the pressure has reached and seen these boundaries. Okay, so if you have, furthermore, if you have skin damage around the wellbore or around the fracture, it's basically an additional pressure loss that you get, right? So your plot will come from here and will pump up because of that damage. You have an additional pressure drop because of that. And it's applicable. This is something that you will see being applied in the industry. It's not too ideal. It's really happening in the industry. So here you can see the linear flow regime happening with the half slope. So if you were to plot a line from here to here, right, 2 by 1, so I'm sure that you will have that half slope type of behavior. See, and that's what you call linear flow. Now, bilinear flow, it has, you know, if you plot 2 by a half, let's say this, more or less, I'm just, and again, my apologies for my drawings, but this quarter slope, like you observe here, is because you have 2 linear flows. So you have 1 linear flow inside of the fracture like this, so that the fracture doesn't have infinite conductivity. Therefore, it experiences some pressure drop along the wings. So you have that combined with a linear flow. That's what gives you a quarter slope, and then you have here the half slope for linear transient flow. And this is very important when you analyze unconventional wells or multi-fracture wells, because you know you have this specialized plot as well. You have, if you, as I mentioned earlier, if you plot, you know, linear flow is proportional to square root of time. So if you plot normalized pressure over here, or rate normalized pressure, RMP, versus square root of time, you will get this type of plot. And wherever your data behaves, sorry about that, wherever your data behaves more or less linear, as shown by this line, is where you have linear transient flow, right? Over here, the linear flow ends and then becomes boundary dominated, but this is not really boundary dominated, and we'll talk about that in a minute. And if you have, you know, if you have a variable pressure and rate conditions, what you can use is the superposition time. for linear flow is a manipulation of the time just to get you to see this behavior. Now, this is important because if we get the y-intercept from this trend, we can get skins, we can get, foremost, we get this value, a square root of k. You will see everywhere, a square root of k tells you about the contacted area by the fractures, and square root of k is the square root of that permeability around the fractures, or if permeability of the SRB, if you will, okay? This is how you get it. And then this m is the slope of this line. You see? So rate transient analysis is very handy because we are using concepts that we will typically use or normally use for pressure transient in analysis in order to get some things from the reservoir. This is another example of using the special square root of time. Notice that, you know, the linear trend is almost obvious. Once you get this slope, you can calculate, you know, if it's constant rate, you have these equations available for you. If it's constant bottom hole flowing pressure, you have these equations for you to, you know, to play with. And all of that, you see this m, again, is the slope, and you get it graphically, okay? So it's really a powerful way to estimate some parameters based on your data. You don't even have to run a model at this point. Of course, you know the equations, but you don't have to run a model yourself to get all of these estimates. But the truth is that, you know, you have some regions over here that at some point are going to contribute, okay? But for now, let us assume that the fracture did actually or effectively, you know, simulated this region. So we can simply take the previous model, right? And then collect more and more and more and more, and then join them together. And that this looks like a multifractal horizontal well, right? It's not really simple yet powerful concept. So what this requires, though, is that you have average properties. You at least have some knowledge about what's going on at every stage, right? Or if you wish, you can just simply say, my average properties look like this, so that all of the stages will look like the same. And then, therefore, you only have to deal with one stage. Okay, so for that approach, you will also assume that fractures are similar or have similar dimensions. And the stage will produce more or less the same amount of fluids, which we know because of the heterogeneities and variability in rock properties in the subsurface. Perhaps it's not a good assumption, but it's really good enough. Let me tell you, it's really good enough. Then we also will ignore that, you know, pressure drop along the lateral is not really as significant as the pressure drop between the reservoir and the wellbore. It's very versatile. So there's no denying that using this type of models is very versatile. It's very easy to implement. The equations are typically used, typically easy to handle. Some of them are not as easy, but still tractable. Still something you can do yourself. And it's being proven to be a very powerful technique because it's able to capture all that's happening at the reservoir level, excuse me, using physics-based modeling. Okay, so it's not like material balance that is a zero-dimensional equation where you only deal with average pressures. No, here you're dealing with your reservoir properties, you're accounting for your completion properties, your fracture properties, etc. Flow regimes will look like this. And remember that I told you, we talk about the linear flow only, that Wattenberger assumed that flow within the fracture really doesn't have any gradient because the conductivity is infinite. Well, in reality, you will have linear flow in the fracture, linear flow around the fracture with a little bit of elliptical flow, and then you find fracture interference flow. So that fracture interference flow is really what defines your SRB, right? So when one fracture sees the other one, or pressure depletion from one fracture sees the other one, it's really your boundary, right? you can draw a boundary like this, and then production will begin to, will start to flow from the matrix into the SRB. So this is why it's called fracture interference, and then a late compound linear flow. Excuse me. This is what it means. You have linear flow from here, linear flow from here, and linear flow from here. So this makes a lot of sense, right? So if flows can be modeled as compound linear flows, you can basically take a multifracture well and then assume that, it has 3 different regions. You have the fracture, you have the SRB, and then you have the matrix, right? This is a very simple model in which you can represent a fracture stage like this. So here is your matrix, here is your SRB, and here's your fracture, right? So in a sense, you are combining 3 different linear flows, which is valid so long as the SRB, or so long as you can guarantee that all of the cracking happening here in this region, all of the fracturing happening here in between fractures was effectively done, so that this region was effectively stimulated, right? So as long as this condition is valid, we can apply this model. And then simply multiply the results by the number of fractures or stages we have. Fracture can have infinite conductivity, or they can have finite conductivity as well. It's up to the user. And then, you can see here that this is a vertical well, but in reality we have a horizontal well, right? So that is, we can model, if this is the fracture and then the well is, the well is over here like this, right? We have the well. So basically we have flow coming this way, linear, and then it really becomes like, I would say 2-dimensional, right? So we model this, or the linear model models this as a vertical well, which has an additional skin over here, okay? To represent the pressure loss caused by this shocking skin factor. That's what it's called, shocking skin factor, very common. And of course, this model accounts for matrix production from the matrix, which the original Wattenberger does not. And again, it assumes that stages or the spacing between the fractures were effectively and fully stimulated. The application for this model, ideally for tightly spaced clusters. And this is how the type curves will look like. I did some of this for my research while at school. So here is your expected pressure behavior without that skin factor that I just mentioned. When you add that convergent skin or choking skin, you see that the solution matches that of numerical data. And then you have your quarter slope here. You have your half slope, which is SRB linear flow, and then almost a unit slope, which is fracture interference flow, and then you have something ongoing here. In the case of my research, this deviation was because of pressure dependent properties. The same happens with this plot. This is a bit of BC slide, has many things, but really all that I wanna show here is that you can use production rate and time to determine your flow regimes. And we're gonna see it towards the end of the presentation. So here you have the half slope behavior of linear flow, right? If you have bilinear flow, meaning that the fractures are experiencing linear flow as well as the SRB, you will see a quarter slow over here. So that tells you that the fracture conductivity is low. Then you have a transition region. Remember, we go from fracture interference into matrix going into the SRB, flow from the matrix going into the SRB. So that's why it's called transition region. And then we have a second linear flow, or a third linear flow, I should say, from the matrix, right? So there are 3 different, or at least 4 different flow regimes that can be captured by analyzing pressure data. And this is reflected over here. Now, it's interesting that in this plot, Dr. Blasingame compares what really happens, which is I think this line, which what you the solid line, which with what you would predict using the Klein curve analysis, right? Which is the yellow band or frame over here, this one. So you see the difference. There is a difference because this is log. You don't see it as clearly, but in Cartesian, you will see that there's a lot of difference. So he calls it the poor man's EUR because it's overestimating the potential, production potential of that well. Now, in 2013, Dr. Salgado and Louis Matar, I know Louis Matar, they introduced the 5-region model. Basically, the 5-region model says, you know, sometimes it's not true that you are able to fully simulate the space between, or the rocking between fractures. So it's better to, you know, to assume that the simulation didn't go all the way through and replicate the model. This is just an example for true fractures, just to tell you that this is what the 5-region model stands for. So you have the true linear flow model that we saw earlier, plus two additional linear flows happening around the hydraulic fracture. And then this is why, I mean, hence the name of 5-region model, right? So you have 5 linear flows. And again, fracture can have finite conductivity and the same approach. You have here a vertical well, then you have to convert it into a horizontal well using the shocking skin factor. And you know, the main point here is that it does not assume fully simulated stages, which is very convenient. And this is ideal for widely spaced cluster or stages. And you know, there are analytical models, analytical solutions for both 5-region true linear flow model. I personally use them. And there are also numerical simulations. There are plenty of them. This is one example from Kappa. And here you can see you have a horizontal well with data to it. And this is your field data. And this is your simulation. And see how different they are a little bit, but then they more or less match, and then you can run your production forecast and tell how much are you going to produce after certain amount of years. Here is like 12, 13 years perhaps. That's the point, right? So how, this is a challenge that we're going to address later. How can we forecast production from such complex systems with little to none data? Like, in unconventional reservoirs, 1 year worth of production is very little. So it's challenging. But anyways, the point here being that, you know, you can have analytical models or numerical models for these 5-region or true linear flow models for you to model unconventional or multifractal horizontal wells. But you also have numerical models and more complex numerical simulations. And, you know, you can be as inventive as you want, and you can add as many natural fractures as you want. You can add, I mean, numerical models, you can do anything with them, right? You can create very complex models that will match your data. But here, the point is, simplicity is the ultimate sophistication. I love that quote from Da Vinci. Simple is better. But it's not too simple. Simple enough to capture physics, not complicated, not too complicated that nobody can use it. You can do, you know, you can reproduce your data using complex models as this, but in the end, they will work for that one well. It's not, they are not, you will not be able to extrapolate those results for entire field. You will not be able to forecast production from a well that hasn't been drilled yet, right? So getting those type well analysis, it's very, very important also for economic reasons. I'll show you next. So this is the last part of my talk. Is about the field case study. So given the time constraint, I'm gonna go as quickly as I can. I probably will take 5 more minutes. Watek, so hope that's not a problem. So I'll do my best to keep on track. Okay. Okay. You know, days ago, I think a couple of months ago, we were discussing all of these topics with an operator here in the Eagle Ford, a big successful company that operates out of several counties in the Eagle Ford, and we were discussing production performance drivers, right? Like we have seen, like completions and fractures, dimensions, etc. And then they say, okay, here is the data for one of my wells. Here it is. What can you do about it? And oh, by the way, I dearly ask you not to use this data. This is proprietary data, so that's the one thing I will really ask you guys to not use. So we have this data, and they ask us, okay, this is a multifracture horizontal well in the lower Eagle Ford. What can you tell me about the reservoir? Or perhaps I should ask you guys this question: what can you tell me about this reservoir? What is happening? What can what can you tell from production, oil and gas, cumulative production? What can you tell about it? One of the things that I could tell right away, but this is just because I've seen problems like this before, is that when you have this type of behavior, when oil and gas are almost proportional to one another, is because you have above ballpoint pressure flowing conditions, right? And look, it's been almost, how long? Almost 4 years, more than 4 years actually, that you're producing above the ballpoint pressure. So you can imagine how steep are the pressure gradients are down in the subsurface. Is this a good or a bad well? Well, we can tell from the cumulative production, but completion-wise, design-wise, it is difficult to tell, right? Just by merely looking at the data. And what is the ultimate recovery from this well? It seems like this well is going to go for a long time, but we cannot really tell whether a fixed number for the estimated ultimate recovery just by looking at it. There are approaches like we can do decline curve analysis, we can do simulation, we can do, what we want to do here is to deconstruct this problem into different pieces and analyze them in the light of production drivers. We saw that, fracture modeling microseismicity is a very, very good way for us to have a sense about how completion went, how the fractures grow, where they are, how long they are, and we can model this by using either a pseudo 3D model, a 2D model, a full 3D model. It's really up to the user, but keeping in mind all of the design parameters that I told you guys before. So that's something very important to have in mind. What are the challenges here when you encounter actual pressure data? What are the challenges? So first of all, keep in mind that multifracture horizontal wells are very complex. In nature, they are very complex. There are so much things happening down there, and your first task is to simplify the model as much as you want. And again, simple, but preserving the physics of the model, preserving the physics of the fluid flow in these type of wells, and preserving the sense of the soundness of the engineering approach. We can consider planar or non-planar fractures, stimulated, non-stimulated rock, or an heterogeneities along the lateral section. And I showed you guys this example before. So how can we model this in a practical way? How can we simply say, hey, I want to average all of this out and determine in that way the true potential of this asset by using a physics-based model? We had decline curve analysis. We talk about it. We discussed their pros. They were very good at predicting future production from conventional wells. They really this is the one thing that sets me down a little bit, is because you don't require any prior knowledge of your reservoir or not any reservoir information to just to fit your data. You can get a fit, but it's just a fit. It doesn't tell you whether or not it's the right solution. So there is a lot of uncertainties involved with decline curve analysis if you don't have the proper knowledge as to which one is right. But Fedkovich in '73, remember the type curves that I showed you, he proved that decline curve analysis is actually rigorous when in conventional wells, excuse me, that are undergoing a boundary dominated flow. And here's again the equation. Here's the equation, but we have more. There are more equations available to us. And you know, this is just one of the many that are there out there in the literature. ARPS, you know, ARPS it was just the beginning. It was just that tiny equation that just exploded, and everybody saw opportunities to forecast the production based on that equation. There are modifications to it. You can talk about power law exponential model. Many people argue that because the time over here has an exponent, you can set it to a half, and then they will model linear flow, translinear flow, exponential, stretch, exponential. You know, you have plenty of them. And in the end, the goal of these equations is to fit your data. And you can, I mean, believe me, the message here is that you can fit your data. Is that the right fit? It's up to you. Is it a good fit to forecast production? Can you extend that fit into the future and then forecast production? That's a little bit dangerous to say yes or no, right? You gotta have a very, very, very good knowledge of the reservoir in order to make those predictions. But here in neither of these models, you can really input reservoir properties. We talk about this, the transient flow, once we get boundary dominated flow, where the material balance are physically valid. This is just a refresher. And then here is the same case. I told you guys that we will review this plot for a multifractal horizontal well. Right now, let us make a cross section of this fracture along its length. This is what we get, right? So this is the slice that we're looking at. You have here the matrix, then we fracture, and then a matrix. The way pressure changes here is this. So you have your initial pressure, then here's where your pressure disturbance or pressure wave is at after a while, after you started producing. So that's what you call transient flow in the fracture, or the first transient linear transient flow in the fracture. And remember that I told you that fractures are typically, have typically high conductivity, so that you rarely see that linear fracture flow. But this is more or less how it goes. But then notice that even though your fracture grading is low over here, look at what's happening at the matrix. Matrix is even over here. It hasn't seen any boundary. It's still transient flow. So therefore, the entire flow, I mean, the flow regime in the entire section, it's transient, right? Because technically you started here and you're still over here. Now let's do another cross section. Now it's across the fracture, right? So we will have this. We'll have the matrix, right? We have the matrix, the SRB, right? Can you guys see it? Matrix, SRB, well, SRB, and matrix. This is what we have here. Matrix, SRB, well, SRB, and matrix. And look at this. So remember we talked about the permeability of the SRB that is better than the permeability of the matrix, at least to some extent, is greater than that permeability. So you will expect to have a little bit more flattened pressure profiles over here, but still this permeability is low. I mean, if we are talking about that, let's say, for example, from what I've seen, permeabilities in the matrix, for instance, in the Eagle 4 can range from 50 nanodarcy to 200 or 500 nanodarcy. Sometimes they go as high as 750 nanodarcy. And then the permeability of the SRB is 20%, 30%, 50% at most higher than the permeability of the matrix. So it's still low, right? But for pressure, I mean, for the purpose of free flow, is good enough for you to flow. So all of the production will be coming from here, most of the production, until you have a pressure gradient over here, or a delta P, which is sufficient for flow to start going into the SRB. That's more or less how it goes. In conclusion, still transient flow, right? And you know that a transient flow, the assumptions of conventional analysis like DCA, decline curves, and volumetrics and material balance equations are not fulfilled. So we gotta be careful when we use decline curves to forecast production from multifracture horizontal wells. Moreover, we have the effect of pressure depletion, right, on properties. Remember, we talked about geomechanics, about the in situ stresses, how they affect fracture conductivity, unpropped fractures versus propped fractures, etc. That's also something you have to take into consideration. So how do we estimate EOR in such a complex situation? So let us go back to our Eagle Ford well. This is what I have. And you know, when we plot, let's do the decline curve for the decline rate over here, this one. So exponentially, this is what I get, which is good. I mean, it's arguably a good fit, right? You know, we have an initial flow rate of 1,000 barrels a day, and then we have this decline rate. It's a daily decline rate. It's really good. Now let's feed the cumulative production over here. So we feed the cumulative production. It's okay. I mean, it has some gaps over here. It might be due to operational things, or, you know, but on average, it's good enough. And this tells me that, you know, this axis is in 1,000 barrels. So this tells me that the recovery is going to be this much, the ultimate recovery, because, you know, when time is high, it's very large, very high, then this becomes almost zero. You can ignore it at late time, very late time. So you are left out with this 500. So the kind of, you know, from this analysis, you got the decline rate per year, and then you estimate EOR. If you were to apply other methods or decline curve methods, probably you will reach to the same conclusions. Okay. And then if you forecast production, so one thing is matching, right? So you calibrated your data with whatever you had in hand. The other thing is taking this into the future, right? That's the challenge, because we don't know if that's the right solution. So we get this and we say, well, it still looks good, right? It still looks good. But you can ask me some questions like, what is the impact of matrix porosity on production performance, right? So, and what about permeability? Does matrix permeability play a role at all? How well did completions go? Like, we have no information about it. Like, is there any indication of geomechanics impacting production? We really don't know, because what we did was just to fit curves. And it turns out that these are the production drivers. So if we think about production drivers, we are left out blind, right? We don't have a really good sense as to what's happening with all of the components that are driving production from this well. So in this part, and this section, I'm going to use the 5-region model. Okay. So for the 5-region model, you know, I use a computer implementation for it and to review what's happening at my well. This is the well, and this is the location of the well. And of course, if I'm going to use a physics-based modeling, I would need a physical information about the reservoir, right? Like at least static reservoir properties, fluid properties, so that I have other information to play with. Excuse, what are you seeing my screen?
Yes. Yes.
Okay. All right. Sorry about that. So, you know, if I'm gonna model this well, I need some information about it, like the initial pressure, the thickness or the pay thickness of the location that the well is at, and what type of fluid I have, right? So when I collected all of this information, you know, this is a proprietary software from our company. This is what I get. Remember all the plots that I showed you, all of the diagnostic plots, like if you have a half slope here for the rate versus time in a log plot, the specialized plot of square root of material balance time, flowing pressure. This is an important plot. This one is rates versus cumulative production. So if you plot this on a log plot and then you extend your line for very, very long, which means that the flow rate is very small, then you will get the EOR, same as here. So here we have, well, okay, I'm gonna leave this for last. So here we have the rate normalized pressure and its log derivative. So here you see, do you recall what we talked about when we talk about the flow regimes. So here we have, if I were to plot a 2x1 line, so it's gonna be something like this. Let me see. Oh my bad. So it's gonna be like this, more or less, right? So this one is transient linear flow, right? It's a half slope. What about this one? So if I were to plot a 1x1 line, 1x1, it's more or less like this, right? So this is a unit slope, which indicates fracture interference flow, right? It's not boundary dominated, it's fracture interference. But yet, notice here that these lines are tending to drift apart from one another. This indicates that matrix had just started to contribute towards production. Now, let us focus on this plot. Here's the decline rate. And again, this is what the simulation shows. It's a very, very good fit. And then up to this point is where I have data available for. Beyond that point is your forecast. Basically, remember that the decline curves say 500,000 barrels. Here, the simulation approach is showing 600,000 barrels. So this is actually sensitive values that you're missing because of a bad calculation. Another important thing to notice is that the well is still in transient flow, so we can really see its boundaries yet after 4 years. Contrary to a conventional well that after a few weeks or months that you're able, even weeks, you were able to see the boundaries, reach the boundaries of the well. Here's the specialized plot. You can see the linear trend over here, where the data behaves more or less linearly. And then this is how pressure dropped. Well, okay, and believe me, we still have some of the questions that we did have for the decline curve analysis. Is this the correct solution? Okay, if the information you have is the proper information, that it will be. But if in the absence of information, you will have to do a probabilistic analysis, or you have to run sensitivity analysis. In other words, this is how matrix porosity will affect your production or your cumulative production, right? So you have, this is a lower bound for this matrix, like from the knowledge that you have from that particular reservoir. For instance, you say, I've seen porosity being in the lows 40% or in the high, high side around 10%, so you have variability. And when you compare that results with those, I mean, using these properties, these values, you will see that your prediction that is here could have been this one, or could have been this one, if you had only 2 years of data available for you. So this is why it's very important to account for all of the rate transient analysis procedures, right? Because if you have little data, like up to this point, then you won't be able to know which one is the right forecast, right? You will have so many solutions over here that you really don't know. This is also how the rate will get affected by matrix porosity, and is similar to matrix permeability. This is its effect. Completion efficiency. So how well we create a fracture complexity around the hydraulic fractures, right? So if we had 100% efficiency, which in this case we did, this is the curve that we're gonna follow. So we luckily, or they luckily got it right. Completions went really, really well for this well. Had the completions had gone not too good, like 20%, this is the cumulative production that you're gonna get. And you can argue like, oh yeah, but in the end, you're gonna get more or less the same EUR. It's just 4% off or so. That's not a problem. The problem is that for you to reach to this EUR, you're gonna have to wait like for almost 20 years. And this difference over here, you see this difference in cumulative production? This is money that you left behind, literally. So this is production that you left down in the ground because of a poor completion design, right? So this is significant money. you are making this with a low completion efficiency, whereas you could have been making this or this one with a high completion efficiency. Fracture conductivity, I told you guys that fractures can be considered high conductive beyond this point, beyond the 200 mark, and this is showing it. Here, you don't see the difference between the two curves for 200 and 1000 because they are essentially the same. So beyond 200, doesn't make sense to put more propan or to inject more because that's the most you're gonna get. On the other hand, if your fracture conductivity is low, you will have, problems with early to mid times recovery. But again, the EUR or the final estimate is not too different. In fact, it's just 2% different from what you should get. The problem is here that you're leaving this production behind. So fracture conductivity can be a production driver if it's too low, right? So you guys gotta bear this in mind. Finally, stimulated rock volume. Oh, no, I think I have a couple more. No, I think it's the last one. Stimulated rock volume. This is what the SRB porosity will do to your production, and it makes sense because most of the production we kept talking about it. Most of the production is coming from the SRB. Therefore, changes or variations in that porosity will have a tremendous impact on production because basically porosity tells you or speaks about your ability to store fluids, right? So if you crack the rock, you very well, you create that complexity around the fractures, you will be able to store more and more fluid in those fracture networks. Likewise, SRB permeability is just telling you about the capacity to flow these fluids out, to drive these fluids out of the SRB into the wellbore, right? So, and again, SRB permeability will not have the same impact on EUR, if at all. But again, we do have this difference over here. So, if for this well, if we had a better permeability enhancement in that SRB, we will have a better recovery here over this 3 to 4 year production, 3rd to 4th year of production. But it's still good, still good. And look at the permeabilities, okay? So this is 500 nanodarcies, and this is 2 microdarcies, just to put it in perspective. I have more about this. If you want to read about what we did for this well, make sure you take a look at the paper, at this paper. I can send it to you, and then you can share with the audience if you want. I can share this paper with you all guys.
Okay.
Okay. So conclusions, finally, right? Conclusions. Understanding performance drivers is key. I mean, if we are going to talk about unconventional reservoirs, if we are talking about multi-fracture wells, the least we should do, and this is to respond to your question, Firas, is we need to understand what's really happening at the subsurface level. If we don't have any understanding, it's very difficult for us to talk about predictions, to talk about forecasting, to talk about economical recovery, to talk about economics in general. DCA methods or decline curve methods very useful for conventionals, a little bit useful, perhaps not as useful for unconventionals. We gotta be careful about how we use them in order to forecast production and things of that sort. Physics-based modeling, really, I mean, if you ask me, if you want my honest opinion, I will always go for physics-based modeling for unconventional reservoirs for the reason that I can basically incorporate all of the knowledge that I have about the reservoir, the completions, the fluids, location of the well, regional marks, geology, etc. I can take all that into account into a physics-based modeling, unlike what you can do with a decline curve analysis. Here, this is something that we promote here at our company at Innovate, is cloud-based workflows. So you saw all of the components that that are involved with this type of analysis. You need a geologist, you need a petrophysicist, you need a geophysicist, you need a reservoir engineer, a production engineer, drilling engineer, and whatnot. You need a lot of people looking at the same data, at the same portion of production histories and the same, logs, etc. So it is really our flagship to promote cloud-based workflows. So a single environment where everybody can look at the same data, make the same conclusions, or share ideas, not the same conclusions, but at least they are able to share ideas with others. This is the place. This is the ideal place to be. So cloud-based workflows, the way to go. But ultimately, production optimization, if you will, production forecast is, in a sense, a multidisciplinary problem. There are, we need to change our mindsets when it comes to, it's not even to about unconventional, but any type of reservoir. We need to stop silos. We need to stop looking at drilling engineers as drilling engineers, completion engineers as completion engineers, a production as production. No, this is something that requires a group. This is a group effort. This is a team effort. We need to collaborate with one another in order to get the best production from our assets. Well, and that is particular to unconventional reservoirs. So with that, I would say thank you so much for attending. I am beyond excited for this opportunity. Thank you, Dr. Watek, and everybody in the audience for giving me the opportunity to sharing my thoughts with you, some of what I've done so far. Also, I want to take the opportunity to encourage you all guys to keep it up and keep moving. The industry is gonna come back up. We're going through a really tough time, but we're gonna go out. We're gonna overcome, and we'll be victorious in the end. Here's my information, guys. I'm a very approachable guy. Sometimes people call me Dr. Molina. I'm like, no, I'm Oscar. Come on, call me Doctor. Here, that's my email. You can find me also on LinkedIn. If you have questions, you can ask them to our team at Innovate. I will personally respond to them. And we also have this hashtag on, I think, on Twitter, on LinkedIn. So if you have any questions about what I presented you guys with, feel free to reach out to me. Last comment I have before I forget. Watek, do you think it's possible that we can take a virtual selfie? So if you guys don't mind, I will take at the end a screenshot of the.
I have already taken.
Oh, really? But I wanted to meet you all. I mean,
I will share it with you.
Okay, please do, because I wanna share also with my colleagues and see how awesome
I will share it
guys
on
are.
our website at LinkedIn.
Okay, perfect. You let me know then, Watek. I would really appreciate that. I'm gonna share on LinkedIn. And let's connect. Let's stay in touch. Search me on LinkedIn, and I will of course add your connection request, and we'll stay in touch from there. All right. With that, I will leave you guys. Thank you so much. I'm open for questions. We have still some time, but I would also like to hear from you, hear your feedback, what you think about what I presented. Whether it was useful for you or not? That will be very helpful for me for next time. I invited to present.
Can you hear me, Oscar?
Yes, sir, I can.
Okay, first of all, thank you very much for this great session. Yes, it is a very heavy information, and hopefully in the future we will have more focus through a really learning session instead of 4 hours of lecture. I believe Dr. Wathaq doing a great job to create some of these. He's already starting one of them, hopefully starting on 13th of August. So I'm hoping through you we will have same training course through daily 2 hours for 15 or 14 days. Anyhow, I have a question you on the beginning. That's how you can help to bring the advices, the tools to our great engineers in Iraq, especially in Basra, to help them to understand how they can think, design to using unconventional way to produce the oil and gas. That's one. And the last question from me to you is, do you think there's possibility from your perspective side to help the Iraqi organization here and the engineers through a good cooperation with the companies in the state to really having a great cooperations to do the unconventional designing wells here in Iraq? Do you think you can do that? And finally,
Yes.
thank you very much for all of this.
Thank you, Firas. I really appreciate your feedback. It's very encouraging, and yes, definitely, I definitely look forward to continue in touch or staying in touch with you all. Continuing, looking at more in-depth training session. Yeah, we can definitely look at that. I will be more than happy to be part of it. Here in in our company, there are other talented people. My boss, he is an excellent petrophysicist. He knows it all about petrophysics and unconventionals. We do have our COO, which is an expert in drilling unconventional wells. There's a wealth of knowledge in our company, and we will, not only me, again, I'm speaking for my company, I think we will be more than happy to hold this type of extended training sessions for you to learn, you all to learn what tools to use, how to approach analyzing data from wells. We can definitely do that. Secondly, collaborations. Yeah, we are always open to collaboration. Again, Innovate is promoting we are not anti but we are against silos. We are against being branded as a company that, they know it all, they are unreachable. No, it's not like that. I mean, we are all humans. We are all human beings. We are made with the same flesh. We need to collaborate with one another. That's the only way we're going to succeed. And if COVID hasn't proved my point valid, I don't know what is it going to be, right? So I think this is the right moment that we can definitely explore for opportunities for collaboration more on the technical side. Definitely, we would like to get more involved with what's going on in the Middle East. So yeah, we will be more than happy to explore those opportunities, and we will definitely stay in touch about those. All right. Any more questions, comments? All of those are welcome.
Good evening.
Yeah, hello.
Good evening. Thank you, and thank Dr. Wathaq for arranging and presenting this informative presentation.
Thank you, Muhammad.
It has added a lot of knowledge. Many thanks. May I ask a question about the completion technologies, the plug and the sleeve? My question is about the sleeve technique. Can you please go to that slide?
Yeah, for sure. So where I compare frac sleeves versus plug and perf, right?
Yes.
Okay, let me go through that slide. I think, by the way, I think I'm gonna let you guys have this presentation, the PDF version of it, for Watek. Dr. Watek, I'm gonna coordinate with him about it.
Okay. It would be much appreciated.
Yeah, no problem. Yeah, let me erase this. Okay, there you go, Muhammad. Please go ahead.
Okay. For the frac sleeves, if we it is numbered from 1 to 8. How can we control the injection to only frac the first
okay
section of this
first
sleeve
section or the sleeve? Yes. So you're gonna place your sleeves. Typically you do that using a coil tubing unit. So you place one sleeve and then you start injecting fluids right away. When you frac that section or that sleeve, you close it out. And there are tons. I mean, I was shown. I will see if I can share with you all guys, because we were we were shown some YouTube videos, very cool videos that explains how they work. These things work. It's really high tech. So basically, you install one sleeve, and they have some slots. So you have a liner. And liner has some slots that you pre-install all of these liners with the casing, right? And then you lower your first sleeve, and that sleeve is gonna pass through this slot liner, right? You have like a mandrel. It looks like a screw or mandrel, but it has some
Okay.
slots
Okay.
of a precise dimension, so that the first sleeve will fit right here, at the first location. Then you inject your fluid, and you frag the stage or that sleeve, and then you close it up. The way you close it up, as I mentioned, was typically with a ball.
A ball, maybe.
Draw the ball, you seal it, and then you continue on. Then you install the second sleeve, and you frack it, and you go on. But I think that typically you install all of the sleeves, frack, and then you go backwards. That's more or less how it goes.
So the fracking have to be by CT.
Yeah, sometimes
by coil tubing.
yes, and
Oh.
it truly, because sometimes it's with wireline. You can get away with wireline so long as your well is not too long. No, actually the other way around. But basically, you pump your tool, you pump your wireline tool, right, and then you just pull it out of the well. So there are two types of completion system: the ball activated completion system and coil tubing activated completion systems. This is more or less how that goes. More information about it, specific information that really is proprietary, like NCS, multi-stage, MCS, multi-stage completion systems. That company, they have their own proprietary technology. Baker Hughes has their own, and etc. It really depends on the vendor, on the company.
Oh, okay. Thank you for the illustration.
Yes, sir. My pleasure. Any more questions? Feedback? Do you guys like the presentation? Anything else you would like to see?
Hello.
Hello.
Hello. This is Dunya Zed from Algeria.
Hey, Dunia said. Thank you for joining.
Thanks. Thank you very much for the presentation. It was great to hear you.
Thank you.
But I have a question. But I'm speaking and looking for the further in the future, because we are looking to go to the unconventional reservoir here in Algeria.
Okay.
But it's caused a problem here, and it's an objection on a subject that is very difficult to start it. Well, my question is, with when the fracture are growing by the time, over the time, and after a while, perhaps till after years, how can we control or not control? How is the risk to have imbalance in the subsurface there with the high pressure after over the time?
Yes, that's a very, very good question, Dunia said, and thank you for asking.
Welcome.
It's been a concern, right? It's been a concern that you have such high drawdowns. Perhaps this picture will show it better. We have such high drawdowns over here, but then we have a very high pressure over here, because really you don't get to access all of these part of the reservoir, right? So it's like, so the asset question is like, okay, so when you deplete this well, what do you do with it? Do you just leave it like that, or what do you do about it?
Exactly. That's it. Yeah.
So there are a couple of techniques that are being used here in the States. One of them is to preload wells. So basically, you inject water to raise this pressure gradient up, and then you abandon the well, so that your pressure is more or less as it was or nearly how it was in the beginning. So you will prevent this pressure gradient to have an effect on long-term production, right? Like if after 20 years the well starts flowing all of a sudden, that will be very scary.
Sure,
But
yeah.
yeah, but you can preload the wells. Others will just pump cement, and there are other plug-in and abandonment techniques that I'm not very well aware of, because most of these wells are still producing.
Till now, okay. We didn't met this problem yet, and I hope we will not get it.
No.
Thank you very much. Thank you very much.
You're welcome, Dunia.
Thank you very
You're welcome. By the way, I want to go to Algiers.
You are welcome anytime. You
Oh
are
yeah,
welcome anytime.
thank you.
Yes. Okay. Just let me know, because I meet you.
I
It will be
will.
an honor for me. Thank you very
Believe
much.
me,
Okay.
I will.
Thanks.
You're welcome. Thank you.
Oscar, I just have a comments
Yeah.
on the first question from Engineer Faraz. I know this material is huge and it cannot be covered in one lecture or one course for one day. So I think for better understanding all the aspects of hydraulic fracture, which is almost new to everyone here in Iraq, because we are not familiar with unconventional reservoirs.
Yep.
So I was wondering if you have time later, like 2 hours a day, to deliver online course for a week, 5 business days or 10 business days, like 2 hours a day, to deliver a detailed course about hydraulic fracture. Are you interested in this?
We can, yeah, we can definitely discuss that offline. Watek is a great opportunity. I will be more than willing to do so.
Okay, thank you.
Okay, any more questions, feedback?
Dr. Wafiq, may I ask you a question?
Yeah, call me Oscar. And yes, you can.
Yes.
Okay, given your experience in working in Iraqi fields, how do you see the applicability of hydraulic fracturing in Iraqi reservoirs, and do you see it being common in the near future to make use of such reservoirs?
Oh yeah, I mean, okay. So I haven't had the pleasure to work in Iraq yet. I would love to, though. I haven't had the opportunity to work with Iraqi fields, but I do know what I do know, and this is something that I was made aware of, is that some efforts have already started with unconventionals in the Middle East. Not allowed to comment more on that, but it's something that is definitely in the plans for several countries in the Middle East. So about Iraqi, I will need a little bit more of information as to a reservoir characterization, what type of unconventional reservoirs you have there, in order for me to make an educated guess and not just talk without having the proper knowledge, Muhammad. But it's the same. I will talk about Colombia, my home country, because it's something similar that is happening right now. We are looking for exploiting these resources, because our country, we produce oil and gas, but we're running out of reserves, and most people are concerned about environmental impacts and issues posed by fracturing, hydraulic fracturing. Some of these. Yeah, some of these concerns are basically planted by politicians. So fracking in Colombia had become heavily politicized, but we got to the point where we have to do it. There's no way around, and then we gotta move forward with it. And I think that eventually many other countries will join, because that's the future. So the unconventionals, as one of my professors used to say, unconventionals is the new conventional. So we gotta keep up the pace, and may the governments aware that, and authorities aware that this is how we're gonna go forward.
If you allow me to comment on this question, actually,
Yes, please.
we have in Iraq like some initialization about hydraulic fracture. If you remember yesterday or maybe today, we talked about there is a problem of struggling in water injection in Zubair Formation in West Korna oil field, phase 1. They used to use like high salinity water injection as well as low salinity water injection, but the water does not go through the layer, through the formation. The permeability is somehow high. It ranges from 150 to 200 millidarcy, but there is no water can be injected. That's why they started, I think, 2 or 3 frac jobs in the last 2 years. Horizontal wells, and they started water injection. However, the maximum injection rate, water injection rate through hydraulic fracture does not exceed 4,000 barrels per day.
Okay.
But they have used about in the Iraqi, I think this is the first, the first issue that of hydraulic fracture, the first steps has been applied on the Zubair Formation of West Korna oil field. Mohammed.
Okay, thank you, Doctor. And many thanks to Oscar.
Yeah, thank you, Mohammed. I appreciate that.
I think we reached to the end of this short course. If anyone has questions, they can write to us through our group Telegram. Also about this course, I will put a poll to evaluate this course as the previous courses. So thank you, Dr. Oscar, for your time and your valuable presentations, valuable lectures about this interesting topics. Thanks to everybody who participated in this course.
Okay.
Before you leave,
Can I say? Doctor?
Okay.
Yes.
Ask you to
Dr. Wathaq,
Yes.
this is me, it's Dunya Zed. I want just to thank you thank you very much for giving me this opportunity to be among this group. Thank you very much.
You're welcome. Welcome.
Thanks. That's all.
Okay, thank you, everybody. I'm going to hang out and end the meeting in order to start download the presentation, the full recording. Okay.
I'll send you what take the PDF I'm gonna do some amendments because I had some typos over there. So I'm gonna send you the updated version, sanitized version on PDF for you to distribute with all the attendees.
Okay.
You hear me, Dr. Wathaq?
Yes.
Could you please add to the poll evaluation a space for comment?
Sorry?
You said you would send some poll evaluation on the group. Could I ask you to add a space for feedback and comments?
I will see if I can add this option, but you can always add a comment. Like you can make a replay to the poll and add your comments.
Thank you.
Okay, thank you, everybody.
All right, thank you. Have a great one.
Thank you for everything.
Yeah, thank you. Thank you for attending, Masin.
Bye-bye.
Bye.
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 Bye-bye.
Bye.